Something is missing from the universe. We can see the stars, the galaxies, the swirling clouds of cosmic dust, but the numbers don't add up. Scientists have been running the calculations for decades, and they keep arriving at the same unsettling conclusion. Most of the universe is made of something we can't see, can't touch, and don't fully understand. We call it dark matter, and for all our technological advancements, it remains one of the biggest unsolved mysteries in physics. But what if there was a hidden force linking dark matter to the familiar world we know? A mysterious, invisible force that could be slipping between both realms like a cosmic ghost? Some scientists believe this force could exist, and they call it the dark photon. The idea of dark photons is wild, but it isn't just science fiction. It's a real theoretical concept, and if it turns out to be true, it could rewrite the way we understand reality itself. But what are dark photons, and why do physicists think they might be lurking in the shadows of the universe? To understand this, we need to talk about the invisible threads that hold our universe together. You've probably heard of photons, the tiny particles of light that let us see the world around us. When you turn on a flashlight, photons spill out, bouncing off objects and traveling through space at the speed of light. But what if there were other kinds of photons? Ones that don't interact with regular matter the way normal light does? This is where the idea of dark photons comes in. Dark photons, if they exist, wouldn't behave like ordinary light. Instead, they'd act as a bridge between the ordinary particles we know and the dark matter that fills the universe. Think of it like this. Imagine you're in a dark room with a one-way mirror. On one side of the mirror, there's the visible world, everything you can touch, see, and measure. On the other side, there's an invisible world, something hidden from our view. If dark photons are real, they could be the key to breaking through that mirror. The big question is, how do we prove they exist? That's where things get tricky. Because dark photons wouldn't interact with light in the way regular photons do, we can't simply shine a beam and expect to see them reflected back. Scientists have had to come up with clever ways to try and detect them, using high-energy particle accelerators, deep space observations, and even experiments designed to look for tiny, unexplained shifts in the forces that govern our universe. One of the most exciting possibilities is that dark photons could explain why dark matter has remained so elusive. Right now, dark matter is a huge mystery. We can see its effects, like the way it bends light from distant galaxies or the way it seems to hold clusters of stars together, but we don't know what it's made of. Some theories suggest that dark matter could be interacting with itself through a hidden force, and dark photons could be the carriers of that force, much like regular photons carry electromagnetic forces. This idea has huge implications. If dark photons exist, they could provide a way for dark matter to interact with normal matter, something we've never been able to detect before. It would mean that the universe isn't just split into normal and dark matter, but that there's a hidden connection between the two, waiting to be uncovered. So, where do we stand in the hunt for dark photons? Some experiments have already started looking for signs of their existence, but the results so far have been inconclusive. That doesn't mean they don't exist, just that we haven't found them yet. In science, some of the biggest discoveries take decades, even centuries, to confirm. The search for dark matter itself has been going on for nearly 100 years, and we're still trying to figure out what it is. But what if dark photons don't exist? What if this whole idea is just a dead end? That's a possibility too. If dark photons aren't real, then we'll have to go back to the drawing board to figure out why dark matter behaves the way it does. But even if we don't find dark photons, the search itself could lead us to other groundbreaking discoveries, ones we haven't even thought of yet. Imagine for a second that dark photons are real, and that one day, we build an experiment capable of detecting them. What would that mean for our understanding of the universe? It would mean that the forces shaping our world are more complex than we ever imagined. It would mean that the so-called dark universe isn't separate from ours. It's just hidden in ways we're only beginning to understand. The hunt for dark photons is far from over, and with each new experiment, we get closer to answering one of the biggest questions in modern physics. Are we on the verge of uncovering a hidden force of nature? Could dark photons be the missing link between dark matter and the world we know? Or are we chasing shadows in a universe that still holds its deepest secrets just out of reach? The search for dark photons isn't just a side project for physicists, it's one of the most important investigations in modern science. If we can prove they exist, it would be a breakthrough on the level of discovering the Higgs boson, or even the theory of relativity. It would change everything we know about fundamental physics. But to understand why this discovery would be so groundbreaking, we need to go deeper into the physics behind dark photons and how they could fit into our understanding of the universe. At the core of the idea is something called the Standard Model of Particle Physics. This is basically the rulebook that describes all the known particles and forces in the universe. It explains how atoms form, why light exists, and how particles interact with one another. But there's a problem. The Standard Model can't explain dark matter. It doesn't even acknowledge that dark matter exists. That's a huge issue because dark matter makes up about 85% of the matter in the universe. Imagine trying to explain the ocean while ignoring most of the water. That's where we're at with physics right now. Dark photons could be the missing piece of the puzzle. If they exist, they could be the key to expanding the Standard Model to include dark matter. Right now, we know that regular photons are responsible for electromagnetism. They allow charged particles to interact and are the reason we have light, electricity, and magnetism. But what if dark matter has its own version of this force? What if dark photons are carrying a type of electromagnetism that only affects dark matter? That's one of the biggest hypotheses scientists are exploring. Think of it like this. Imagine you're in a room with a bunch of invisible people. You can't see them, you can't touch them, but you can hear them whispering to each other. That's kind of like what dark photons might be doing. They could be allowing dark matter to interact with itself in ways we can't directly observe. This would explain why dark matter behaves so strangely. We can see that it holds galaxies together, but it doesn't seem to interact with normal matter the way other forces do. If dark photons exist, they could be mediating those interactions in a way we just haven't detected yet. So, how do we find them? Scientists have designed several experiments to look for dark photons, but it's not as simple as pointing a telescope at the sky and hoping to see them. Because dark photons wouldn't interact with normal matter in obvious ways, we need to be incredibly clever in how we search for them. One approach involves particle accelerators, like the Large Hadron Collider. The idea is to smash particles together at high speeds and look for missing energy that might be carried away by dark photons. If we see energy disappearing in a way that can't be explained by known physics, it could be evidence that dark photons are real. Another approach involves looking at how regular photons behave in certain conditions. Some theories suggest that dark photons could mix with normal photons under the right circumstances. If this is true, we might be able to detect small changes in how light moves through space. Some experiments are already searching for these subtle shifts, hoping to catch a glimpse of this hidden force at work. But there's another intriguing possibility. What if dark photons aren't just affecting dark matter? What if they're affecting us in ways we don't even realize? Some scientists have proposed that dark photons could create tiny shifts in the forces we take for granted, like gravity or electromagnetism. If this is true, then dark photons might be responsible for unexplained anomalies we've seen in physics experiments. For example, there have been odd discrepancies in measurements of fundamental constants, like the magnetic properties of electrons. Some researchers believe these tiny inconsistencies could be caused by interactions with dark photons. If that turns out to be the case, then dark photons aren't just a theoretical curiosity. There's something that could be influencing the very fabric of our reality. This raises a mind-blowing question. Could dark photons be responsible for unexplained cosmic phenomena? There are strange occurrences in space that don't quite fit with our current understanding of physics. Mysterious bursts of energy, unexplained fluctuations in cosmic background radiation, even the strange behavior of some stars. What if dark photons are playing a hidden role in all of this? Some researchers have even suggested that dark photons could be linked to one of the most puzzling cosmic mysteries of all, fast radio bursts, or FRBs. These are incredibly powerful flashes of radio waves that come from deep space, and we still don't fully understand what causes them. Could it be that dark photons are behind these strange signals? It's a wild idea, but until we know for sure, everything is on the table. The hunt for dark photons is still in its early stages, but the potential discoveries are enormous. If we find them, we won't just be solving the mystery of dark matter, we could be opening the door to an entirely new branch of physics. Imagine what that could mean. It would be like discovering a new dimension, a hidden layer of reality we never knew existed. Right now, we're at a crossroads. The experiments are running, the theories are being tested, and the evidence is slowly building. Will we find proof of dark photons in the next decade? Or will this be another mystery that takes generations to unravel? One thing is certain, the universe is hiding something from us. And dark photons might just be the key to finally unlocking its secrets. If dark photons exist, they wouldn't just be a minor footnote in physics. They would force us to rethink everything we thought we knew about the universe. They could provide a long-sought-after link between the visible and the invisible, the known and the unknown. And if that connection exists, then what else are we missing? Could there be an entire set of forces, particles, and interactions hiding just beyond our reach? One of the most exciting possibilities is that dark photons could explain why dark matter behaves so strangely. Right now, we know that dark matter is out there because of its gravitational effects. It bends light from distant galaxies, it influences the rotation of stars, and it holds galaxy clusters together. But what if there's more to it? What if dark matter has its own hidden interactions, governed by a force we've never seen before? This is where dark photons come in. In the standard model of particle physics, forces are carried by particles. The electromagnetic force is carried by photons. The weak nuclear force is carried by W and Z bosons. The strong nuclear force is carried by gluons. But dark matter doesn't seem to interact with any of these known forces. It doesn't emit light, it doesn't have an electric charge, and it doesn't seem to participate in nuclear interactions. This has led some scientists to propose that dark matter might have its own force, one that operates separately from everything we've seen so far. Dark photons would be the messengers of this new force, allowing dark matter particles to interact with each other while remaining invisible to us. This idea is sometimes called a dark sector. In other words, dark matter might not just be a bunch of invisible particles floating around. It could have its own complex structure, with forces, interactions, and maybe even entire, dark atoms, bound together by dark photons. This would mean that the universe is even more complex than we ever imagined, with two parallel realms of physics coexisting side by side. If this is true, then detecting dark photons becomes even more important. Not only would they help us understand dark matter, but they could reveal an entire hidden layer of reality. Imagine if we could one day manipulate these forces the same way we manipulate electromagnetism today. Just as humans learned to harness electricity to build civilization, could we one day harness dark photons to unlock new technologies? Could they be used for advanced space travel, energy generation, or even communication across vast distances? Of course, we're still far from that point. Right now, the challenge is proving that dark photons exist at all. Scientists have devised multiple ways to search for them, but each approach comes with its own difficulties. Some experiments involve high-energy collisions and particle accelerators, where researchers look for tiny discrepancies in how particles behave. Others involve astrophysical observations, searching for anomalies in the way light and gravity behave on cosmic scales. One particularly interesting idea is that dark photons might cause tiny shifts in the properties of ordinary particles. For example, some experiments suggest that electrons and muons, two fundamental particles, might behave slightly differently than expected. If dark photons are interacting with these particles in ways we haven't accounted for, it could explain these strange results. Another approach involves looking at the cosmic microwave background, the faint afterglow of the Big Bang. This radiation has been traveling through space for billions of years, and any unexpected distortions in it could be a clue that dark photons are at work. If we find patterns that don't match what standard physics predicts, it might be evidence that dark photons have been influencing the universe since the beginning of time. But what if we never find them? What if, after decades of searching, the experiments come up empty? That would be a major blow to the idea, but it wouldn't necessarily mean dark photons don't exist. It could simply mean that our current methods aren't sensitive enough, or that we're looking in the wrong place. The history of science is full of discoveries that took much longer than expected. The Higgs boson was theorized in the 1960s but wasn't discovered until 2012. Gravitational waves were predicted by Einstein over 100 years ago, but we only detected them recently. If dark photons are real, then it's only a matter of time before we find them. And when we do, the implications will be staggering. It could mean that dark matter is more than just a cosmic placeholder. It could be an active, dynamic force shaping the universe in ways we never imagined. But there's an even deeper question lurking in all of this. If dark photons exist, then what else is out there? Could there be other hidden forces, particles, and interactions we haven't even considered? Some theories suggest that dark photons could be just the beginning, that the universe could be teeming with unseen phenomena waiting to be discovered. What if dark photons lead us to something even bigger? Could they be a stepping stone to a deeper understanding of the fabric of reality? Could they point us toward a new theory of physics that goes beyond even our wildest predictions? Right now, we don't have the answers. But one thing is certain, the universe isn't done surprising us. If dark photons exist, then we may be on the verge of uncovering an entirely new layer of physics, one that has been hiding in plain sight for the entire history of the universe. But the implications go beyond just understanding dark matter. If dark photons are real, then they could change our fundamental understanding of forces, interactions, and even the nature of reality itself. One of the biggest questions that physicists are asking is whether dark photons interact with regular matter at all, even in small ways. Right now, we assume that dark matter is completely separate from the forces we experience daily. It doesn't respond to electromagnetism, it doesn't participate in the nuclear forces, and it only interacts with gravity. But what if dark photons provide a tiny bridge between the dark sector and our own? This would be a game changer. If dark photons have even the smallest interaction with normal matter, then it means dark matter isn't as untouchable as we once thought. It could mean that dark matter is detectable, not just through its gravitational pull, but through tiny effects in the physics we already know. This is one of the main reasons researchers are so interested in finding dark photons. If they exist, then dark matter might not be as invisible as we assumed. Some theories suggest that dark photons might have a slight, mixing, effect with regular photons. This means that, under the right conditions, a normal photon could briefly transform into a dark photon and then back again. This wouldn't happen often, but if it does, then it means dark photons are subtly affecting the way light behaves across the universe. This could explain certain unexplained cosmic phenomena, like strange fluctuations in the cosmic microwave background, unexpected dimming of distant stars, or unexplained anomalies in how light travels through space. But there's another possibility, one that is even more mind-blowing. If dark photons interact with regular matter in any way, then it raises the question, could they be influencing life? Could dark photons have subtle effects on biological systems, or even consciousness itself? This might sound like pure speculation, but physics has a history of surprising us. Quantum mechanics, for example, has shown that particles can be in two places at once and that the act of observation can influence reality. If dark photons are a real force, then who's to say they don't have hidden effects that we've never even considered? Some researchers have even suggested that dark photons could be responsible for some of the unexplained anomalies in particle physics. There have been experiments where particles behave in ways that don't match theoretical predictions, such as the slight difference in the magnetic moment of the muon, which was recently measured to be slightly different from what the standard model predicts. Could this be evidence of dark photons subtly influencing particle behavior? Some physicists think so. And if dark photons do exist, then how did they come to be? Were they created in the early universe, just like regular photons? If so, then they might have played a role in shaping cosmic history. They could have influenced the formation of galaxies, the distribution of dark matter, and even the fundamental structure of space-time. If dark photons were present in the early universe, then their effects could still be detectable today, hidden in the fine details of how the cosmos evolved. One of the most exciting ideas is that dark photons could provide a new way to study the invisible universe. Right now, almost everything we know about space comes from observing light, visible light, infrared, X-rays, radio waves, and so on. But if dark photons exist, they could open up an entirely new method of observation. Imagine if we could build a detector sensitive to dark photons, allowing us to see the dark matter structures that shape the cosmos. It would be like suddenly gaining a new sense, like going from being blind to seeing for the first time. This would revolutionize astronomy. We might be able to map the hidden structures of the universe, revealing dark matter in ways we never thought possible. We could detect new types of cosmic phenomena that are currently invisible to us. We might even find that the universe is far stranger than we ever imagined. And there's one more possibility that can't be ignored. If dark photons exist, and if they interact with dark matter, then what else could be out there? Could dark matter itself contain complex structures, galaxies, planets, or even life? Right now, we think of dark matter as a featureless, invisible substance that simply provides extra gravity. But what if it's more than that? What if dark matter has its own hidden complexity, its own rules of physics, and its own unknown civilizations? We have no way of knowing yet, but finding dark photons could be the first step toward answering these questions. Right now, our understanding of the universe is like a puzzle with half the pieces missing. We've built a picture using what we can see, but dark photons might be the missing link that connects everything together. The search continues. Physicists around the world are running experiments, analyzing data, and pushing the limits of what we know. The answer could come tomorrow, or it could take decades. But one thing is certain, the universe is hiding secrets from us. And if dark photons exist, they could be the key to unlocking one of the greatest mysteries of all time. As researchers dive deeper into the theoretical and experimental world of dark photons, they are faced with the monumental task of detecting something so elusive that it might be hidden in the tiniest interactions of the universe. The search isn't just about finding a new particle. It's about potentially rewriting the laws of physics that have guided us for centuries. The complexity of dark photons lies in the fact that they wouldn't behave the way normal photons do. Since they are hypothesized to interact weakly with ordinary matter, they might never show up in any direct observations or high-energy experiments like the ones we use to study visible particles. Instead, they might require incredibly sensitive equipment, pushing the limits of our technological capabilities. But this doesn't mean the search is hopeless. It just means we need to think outside the box. One way to detect dark photons is by looking for anomalies in particle accelerators. Particle accelerators, like the Large Hadron Collider, LHC, are capable of smashing particles together at incredibly high speeds, producing vast amounts of energy. When this happens, particles that we normally can't detect might be created. The idea is that if dark photons exist, they could be produced in these high-energy environments, and then decay into other particles we can detect. These decays could create telltale signs, subtle shifts in the behavior of particles, which would allow physicists to pinpoint dark photons' existence. This approach has already led to some tantalizing hints. In experiments at the LHC, unusual particle behavior has occasionally been observed. While many of these anomalies can be explained by known physics, some continue to baffle researchers. Could these discrepancies be the result of dark photons interacting in ways we didn't expect? The possibility is there, and each unexplained event brings us one step closer to understanding the true nature of the universe. However, detecting dark photons isn't just about particle accelerators. Another promising avenue of research involves astrophysical observations. Dark photons could affect the way light behaves across cosmic distances. For example, they could interact with photons traveling through space, causing distortions in the light we see from distant stars and galaxies. If we were able to measure these distortions with enough precision, it could be a direct signal of dark photon interactions. One of the most intriguing possibilities here involves the study of cosmic microwave background (CMB) radiation, the afterglow of the Big Bang. The CMB contains a wealth of information about the early universe, but it is also a delicate signal that can be influenced by many factors, including the presence of dark photons. If dark photons exist, they might have caused small variations in the temperature and polarization of the CMB that we haven't been able to detect yet. Finding these variations could unlock an entire new understanding of the early universe, shedding light on the origins of both normal and dark matter. In addition to the CMB, researchers are also looking at the way light behaves near black holes and other massive cosmic structures. Black holes are known to distort spacetime, bending light, and even trapping it within their gravitational pull. But what if dark photons are also playing a role? If dark photons exist, they could influence how light interacts with the gravitational fields of black holes, potentially leaving behind patterns or signatures that we could observe with advanced telescopes. It's important to note that these approaches are still in their infancy. The tools and technologies required to detect dark photons are still being developed. Scientists need to collect more data, refine their theories, and come up with new experimental designs that are sensitive enough to detect the faintest of signals. However, the potential rewards of success are immense. If we can detect dark photons, we would not only uncover the true nature of dark matter but also unlock the secrets of a whole new realm of physics, one that operates behind the curtain of the visible universe. One of the most exciting ideas that comes with the detection of dark photons is the potential for new technologies. If we can learn to manipulate dark photons, it could lead to breakthroughs in fields ranging from energy production to communication. Dark photons might be a new way to transfer energy without loss over vast distances. They could provide a new form of communication that doesn't rely on conventional electromagnetic waves, potentially allowing for faster and more secure transmission of information. The possibilities are boundless. The discovery of dark photons could even reshape our understanding of space and time itself. If dark photons interact with the fabric of space, they might offer clues about the very nature of gravity, the structure of the universe, and the interplay between the quantum and cosmological scales. Perhaps dark photons are a missing link in the search for a unified theory of physics, one that could reconcile general relativity and quantum mechanics. This has been the holy grail of physics for over a century, and dark photons might be the key to unlocking that final frontier. But beyond all of this, dark photons represent something even deeper, the possibility that we are just beginning to understand the true nature of the universe. We often think of physics as a finished puzzle, where all the pieces have been placed, and all the questions answered. But the more we discover, the more we realize how much we don't know. The search for dark photons is a reminder that the universe is full of mysteries, and that science is an ongoing journey of discovery. If dark photons exist, it would be one of the most profound breakthroughs in the history of science. It would not only open the door to understanding dark matter, but it would also illuminate the very structure of reality itself. The possibilities are endless, and the excitement surrounding this field of research is palpable. While we may not have all the answers yet, one thing is clear: dark photons have the potential to rewrite the laws of physics as we know them. And perhaps, one day, when we finally unlock the secrets of dark photons, we'll find ourselves staring at a new chapter in the book of the universe, one filled with discoveries that we can't even imagine yet. The prospect of discovering dark photons brings us to the precipice of an entirely new era in physics, one where our understanding of the universe may dramatically shift. What dark photons represent isn't merely a new particle to study, but an entirely new framework that could help us make sense of the most perplexing aspects of the cosmos. For decades, we've been caught in the grip of two competing ideas: the elegant theories of the Standard Model of particle physics, which describes the forces and particles we can observe, and the realization that a vast portion of the universe seems to be invisible, dark matter. If dark photons are indeed real, it could help bridge these two worlds, the observable and the hidden, offering us a way to understand the dark matter that holds galaxies together, but which we can't see or directly interact with. This means we could finally start to answer questions that have been plaguing cosmologists and physicists for years. For example, why do galaxies rotate faster than we would expect based on the visible matter we can observe? Why do galaxy clusters behave in ways that suggest there's more mass present than what's visible? Dark photons may hold the key to finally solving these cosmic puzzles. But let's take a step back and consider the bigger picture. Dark photons may not only help us understand dark matter but also give us clues about the very nature of fundamental forces themselves. At the heart of physics is the search for a unified theory, one that links all forces of nature together under a single, cohesive framework. We already know that electromagnetism, gravity, the strong nuclear force, and the weak nuclear force govern the behavior of particles and matter. But these forces don't seem to get along. Gravity, for example, doesn't fit neatly into quantum mechanics, and the strong force that holds atomic nuclei together doesn't easily align with the other forces. Could dark photons provide the missing link? Dark photons could represent a fifth force, something that interacts with dark matter and maybe even the other forces we know, but in ways that are currently invisible to us. If dark photons are a part of this hidden realm, then they could provide a bridge between the four forces we understand and the mysteries of the dark sector. They might give us a pathway to finally reconcile quantum mechanics and general relativity, two pillars of modern physics that have resisted attempts at unification for over a century. There's another level to this too. If dark photons exist, they may not just be a product of the universe's early history. They might have lasting effects on the behavior of the universe today. They could play a role in the ongoing expansion of the universe, the formation of galaxies, or even the behavior of black holes. There are hints that the universe's evolution has been shaped not only by the forces we can see, but by those we can't. The discovery of dark photons could add a new dimension to this story, shedding light on the very forces that are still driving the universe forward. This leads us to another fascinating idea. What if dark photons could be the key to unlocking a new chapter in the story of dark energy? We know that dark energy is responsible for the accelerated expansion of the universe, but we don't know what it is or how it works. Could dark photons somehow be linked to this mysterious force, affecting its behavior in subtle but crucial ways? What if the hidden influence of dark photons is a crucial ingredient in the ongoing expansion of the cosmos, interacting with dark energy to drive the universe apart at an accelerating rate? This possibility would transform our understanding of cosmology, and could completely reshape our conception of the universe's fate. Moreover, dark photons might help explain some of the most perplexing anomalies we've observed in space. For instance, some astrophysicists have observed certain patterns in the cosmic radiation and certain oddities in how light behaves at high energies. Could these anomalies be caused by dark photons? If dark photons exist, they could influence the behavior of light across vast distances, leaving behind subtle clues that we might only now be beginning to detect. If researchers can find these clues, we might be able to uncover hidden patterns in the cosmos that have gone unnoticed for centuries. At this point, it's important to recognize that the discovery of dark photons, like many of the most profound breakthroughs in science, will likely not come through any single experiment or observation. It will require a vast, collective effort from scientists around the world, using an array of techniques, from particle accelerators to astronomical observations, to piecing together the evidence bit by bit. However, the potential rewards for solving the mystery of dark photons could be immense. Beyond the scientific triumph, the practical implications of understanding dark matter could revolutionize many fields, from energy production to computing to transportation. Just as we harness the forces of electromagnetism for our daily lives, understanding dark matter could open up entirely new fields of technology. We are at the beginning of a new era. If dark photons exist, they are likely just one piece of a much larger puzzle. Understanding them could open up a treasure trove of mysteries about the universe, from the fundamental nature of matter and energy to the unexplored realms of the cosmos that lie just beyond our current understanding. The search for dark photons is more than just a scientific endeavor. It's a quest to understand the very fabric of the universe. In the coming years, we are likely to see advancements in technology and theory that will bring us closer to discovering whether dark photons are real. With each new experiment, each new piece of evidence, we get closer to uncovering the hidden layers of reality. And when that day comes, it will be one of the greatest moments in human history, a moment when we finally glimpse the dark side of the universe and begin to understand the forces that govern not just the stars, but the very building blocks of existence. But even then, the journey will not be over. Dark photons might be the first step, but there are many more questions to answer. What else might be out there in the hidden, dark sector of the universe? What other particles, forces, or phenomena could be influencing the cosmos in ways we can't yet detect? The possibilities are boundless. And as we embark on this search, we will continue to be reminded that the universe is a far stranger and more wondrous place than we could have ever imagined. As we continue exploring the enigmatic realm of dark photons, we are faced with the realization that we may be standing at the threshold of a profound transformation in how we view the universe. The investigation into dark photons isn't just about identifying a new particle or confirming a speculative theory. It's about opening up new dimensions of inquiry into the very nature of reality itself. The scientific community, after decades of relatively small steps forward, is now on the cusp of potentially one of the most significant breakthroughs in modern physics. As we search for dark photons, we aren't just peering into the shadowy corners of space. We're also looking for the mechanisms that could unravel the deep mysteries that govern the universe. This idea of bridging the known and unknown is central to the quest for understanding dark matter and dark photons. Unlike regular photons, which mediate the electromagnetic force that governs the behavior of visible matter, dark photons are theorized to mediate interactions within the dark sector, the hidden, invisible part of the universe that accounts for the vast majority of its mass. If these dark photons exist, they would represent a fundamental new interaction between dark matter particles, a mechanism that could alter our entire understanding of the cosmos. The discovery of dark photons could offer the key to unlocking the entire dark sector, revealing how it fits into the broader framework of physics. To fully appreciate what dark photons could mean, we have to delve deeper into how they could work. The fundamental properties of dark photons, as theorized, share a striking resemblance to their ordinary counterparts. Just as the photon is massless and carries the electromagnetic force between charged particles, dark photons are expected to be massless and to mediate forces within the dark matter sector. The major difference is that dark photons would interact much more weakly with ordinary matter, making them nearly invisible to our current observational tools. Their very name, dark, stems from their lack of interaction with electromagnetic radiation, which makes them undetectable by traditional methods like telescopes or particle detectors. Instead, their existence might only be inferred through indirect effects, such as their influence on the motion of galaxies, the bending of light around large objects, or the behavior of other cosmic phenomena. One of the most compelling aspects of dark photons is their potential to reveal a new type of symmetry in the universe. Symmetry is a core concept in physics, and it underpins much of what we know about the laws of nature. The standard model of particle physics, for example, relies on symmetries to explain how different forces interact. If dark photons exist, they could reveal an additional symmetry in nature, one that involves the dark sector of the universe. Theories such as gauge symmetry and the idea of hidden sectors predict that dark photons could be linked to the mysterious dark matter particles. This link would be much stronger than the mere presence of dark matter as a passive substance in the universe. It would suggest that dark matter interacts with itself and could even exchange energy in ways that regular matter cannot. Moreover, this hidden symmetry might lead us to an even deeper understanding of the fundamental forces of nature. For example, some theories suggest that dark photons could provide a window into the unified force that ties together gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. As we seek a grand unified theory, GUT, which aims to explain all the fundamental forces within a single framework, dark photons could serve as an essential piece of the puzzle, helping us understand the connections between the visible and invisible parts of the universe. If dark photons are proven to exist, they could potentially offer insight into the elusive theory of everything, providing the bridge that many physicists have been searching for decades. Despite their theoretical potential, dark photons remain elusive, and detecting them is no easy task. The weakness of their interactions with regular matter presents a significant challenge. Unlike visible photons, which can be detected with telescopes or particle detectors due to their strong interactions with matter, dark photons would not leave a straightforward trace. This makes them extremely difficult to observe, and it raises the question, how do we even begin to search for something so subtle and elusive? Researchers are developing a range of experimental approaches to detect dark photons indirectly. One promising method involves using large particle detectors, which could potentially observe the decay of dark photons into other particles. In a scenario where dark photons interact with dark matter, these interactions might produce secondary particles that can be detected. Another approach involves searching for the effects of dark photons on the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. The CMB holds information about the early universe, and any deviation from the expected patterns could be a sign that dark photons are influencing the fabric of spacetime itself. In addition, scientists are exploring the idea of using particle accelerators, such as the Large Hadron Collider, LHC, to produce dark photons in high-energy collisions. These experiments involve accelerating particles to near-light speeds and smashing them together, potentially creating exotic particles, including dark photons, under the right conditions. However, the challenge lies in distinguishing these dark photons from the myriad of other particles produced in such collisions. Given their weak interactions with ordinary matter, dark photons might leave behind only a faint signal, making it difficult to detect them amid the noise of other particle interactions. As difficult as these methods are, the implications of discovering dark photons are so profound that the search is likely to continue with increasing intensity. If dark photons do exist, they could provide the first real connection between the visible and dark sectors of the universe, opening up new avenues for research and exploration. Moreover, understanding dark photons could offer new insights into the very structure of spacetime, revealing hidden dimensions of reality that we have yet to imagine. However, even if dark photons remain elusive for some time, the mere pursuit of this mystery could yield unexpected breakthroughs. Theoretical physics, often driven by intuition and the pursuit of deep understanding, has historically led to advances in technology and new scientific paradigms. Just as the search for the Higgs boson led to the development of new particle detection technologies, the quest to uncover dark photons may spur innovations in scientific instrumentation, computational techniques, and even our broader understanding of the universe. But beyond the immediate scientific benefits, the discovery of dark photons would also challenge our very conception of reality. For centuries, we have built our understanding of the universe on what we can observe, touch, and measure. The discovery of dark photons, if confirmed, would be a reminder that our perception of reality is only a fraction of what truly exists. It would suggest that the universe is far more complex, mysterious, and interconnected than we ever imagined. The search for dark photons is not just about identifying a new particle. It's about expanding our horizons, redefining the boundaries of what we consider to be possible, and unveiling the deep mysteries that lie just beyond our reach. In many ways, the search for dark photons mirrors the broader search for understanding itself, a quest that drives human curiosity and imagination. From the ancient quest to understand the stars, to the discovery of atoms and subatomic particles, and now to the dark matter that makes up most of the universe, science has always sought to push the limits of what we know. The discovery of dark photons could be the next great leap in this ongoing journey, a journey that, though it may take decades or even centuries to fully unravel, will continue to shape the future of human knowledge and our place in the cosmos. As we delve even deeper into the mystery of dark photons, it becomes clear that these hypothetical particles are not just a mere curiosity for physicists. They represent a pivotal opportunity to completely revise our understanding of the universe. The very idea of dark photons challenges our deeply held beliefs about the structure of reality and the forces that govern it. These particles, as theorized, may hold the key to understanding how dark matter interacts, how it connects with visible matter, and how it affects the fundamental fabric of spacetime itself. One of the most striking aspects of dark photons is their ability to unify different theories and frameworks of physics. For many years, physicists have been struggling to reconcile the standard model of particle physics with the mysteries of dark matter. The two realms, while both essential to our understanding of the cosmos, seem to be governed by very different rules. Ordinary matter, which makes up everything we can see, feels the effects of the four known fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. In contrast, dark matter, which makes up approximately 85% of the mass in the universe, doesn't seem to interact with any of these forces in a noticeable way. It doesn't emit, absorb, or reflect light, which is why it's invisible to our most powerful telescopes. Yet, despite this lack of interaction with ordinary matter, dark matter exerts a gravitational pull that is noticeable on the scale of galaxies and galaxy clusters. This has led scientists to propose that there must be some unknown interaction happening within the dark sector, a theory that dark photons could potentially help explain. These particles, as mediators of interactions within the dark sector, might offer a bridge between the invisible and visible parts of the universe, suggesting that dark matter is not as isolated and disconnected from the rest of the universe as it first appeared. The existence of dark photons could also explain some of the most puzzling observations in astrophysics. One of the biggest mysteries is the behavior of galaxies and galaxy clusters. If dark matter only interacts via gravity, it doesn't explain why galaxies rotate the way they do or why galaxy clusters behave as they do. The observed behavior of galaxies, where the outer stars move faster than expected based on the mass of visible matter alone, points to the existence of some unseen mass. The presence of dark photons could help explain these phenomena, as their interactions could potentially provide additional forces that influence the motion of galaxies and their constituents. This could lead to a more comprehensive understanding of the dynamics at play in galaxy formation and the large-scale structure of the universe. In addition to galactic rotation, dark photons might also provide answers to some of the more enigmatic aspects of cosmic microwave background (CMB) radiation. The CMB, which is the afterglow of the Big Bang, contains a wealth of information about the early universe. Any fluctuations or anomalies in the CMB could indicate new physics at play. If dark photons exist and interact with dark matter in a way that influences the CMB, detecting these effects could be crucial for understanding the conditions of the universe shortly after its creation. These fluctuations might be subtle, but if they are present, they could serve as a vital clue in the puzzle of dark matter and dark energy. Another intriguing aspect of dark photons is their potential relationship with dark energy, the mysterious force that is causing the accelerated expansion of the universe. Dark energy is one of the most perplexing aspects of modern cosmology. It is thought to make up around 68% of the universe, yet its nature remains completely unknown. The discovery of dark photons might open a new path to understanding dark energy and its connection to dark matter. If dark photons are a mediator of dark matter interactions, they could potentially have a role in shaping the behavior of dark energy as well. Understanding how dark photons interact with both dark matter and dark energy could provide the key to unlocking one of the greatest mysteries of the cosmos, the nature of the force that is driving the universe apart. The role of dark photons in this context is still speculative, but some theories propose that they could be involved in the phenomenon known as cosmic inflation. This rapid expansion of the universe occurred just moments after the Big Bang, and it helped shape the universe as we know it today. The precise mechanism behind cosmic inflation is still unclear, but dark photons could be a potential candidate for explaining this process. If dark photons exist, they could have played a crucial role in the interactions between dark matter and other forces in the early universe, setting the stage for the expansion that followed. While all of these potential discoveries are exciting, we must acknowledge that the search for dark photons is far from guaranteed. It is one thing to theorize their existence and imagine the implications they would have on our understanding of the universe. It is another thing entirely to find concrete evidence that these particles actually exist. The challenge is immense, and it requires advanced experiments, innovative technologies, and of course time. One of the main obstacles in detecting dark photons is their extremely weak interaction with ordinary matter. As we mentioned earlier, dark photons are theorized to interact very weakly with the electromagnetic force, which means they don't leave behind detectable traces the way regular photons do. Unlike regular photons, which can be detected with sensitive instruments like telescopes, dark photons are expected to pass through ordinary matter without leaving a significant impact. This makes detecting them incredibly difficult, even with the most sophisticated instruments. Nonetheless, there are a number of experimental techniques being developed that could provide a way to indirectly detect dark photons. One such technique involves searching for anomalies in the cosmic microwave background (CMB) radiation. If dark photons interact with other particles in the early universe, they could leave behind subtle imprints in the CMB. By analyzing the CMB with increasing precision, scientists may be able to detect these imprints and confirm the presence of dark photons. Similarly, particle accelerators like the Large Hadron Collider (LHC) are also being used to search for signs of dark photons. In these high-energy collisions, dark photons could be produced, albeit in extremely small amounts. Even if these particles are generated, detecting them amidst the enormous amount of data produced in such collisions is a daunting task. Other experiments are focused on the search for hidden photons, which are similar to dark photons but are theorized to interact even more weakly with regular matter. These hidden photons could reveal themselves in subtle ways, such as by causing shifts in the behavior of other particles or influencing the trajectories of cosmic rays. Researchers are developing highly sensitive instruments to detect these elusive particles, and some have proposed using large arrays of superconducting detectors or even space-based observatories to hunt for hidden photons. Despite these challenges, the search for dark photons remains one of the most exciting frontiers in modern physics. The potential implications for our understanding of the universe are vast, and the discovery of dark photons could lead to a revolution in our comprehension of everything from the behavior of galaxies to the nature of dark matter and dark energy. Even if dark photons remain elusive for some time, the search for them will undoubtedly push the boundaries of scientific knowledge and lead to unforeseen discoveries along the way. As we continue to explore the strange case of dark photons, we are reminded of the beauty and complexity of the universe. The search for these particles is not just about uncovering new physics. It is about challenging our fundamental assumptions and expanding the horizons of human understanding. It is a reminder that, no matter how much we know, there is always more to discover. The mysteries of the cosmos are vast, and with each new theory, experiment, and observation, we inch ever closer to uncovering the hidden truths that lie just beyond our reach. The search for dark photons is a reflection of the ever-evolving nature of scientific inquiry. The journey is just as important as the destination, for it forces us to question what we think we know about the universe and encourages us to push the boundaries of what is possible. Each experiment, each new observation, and each hypothesis brings us one step closer to unraveling the mysteries that have perplexed humanity for centuries. The discovery of dark photons, or even the confirmation of their absence, would represent a monumental leap in our understanding of the cosmos, and could potentially open up entirely new avenues of research. One of the most exciting aspects of dark photons is their potential to help solve several interconnected mysteries in cosmology and particle physics. The mystery of dark matter, the most dominant form of matter in the universe, has been a central puzzle for physicists for decades. We know that dark matter interacts with gravity, shaping the structure of galaxies and influencing the motions of cosmic objects. Yet, despite its overwhelming presence, dark matter does not seem to interact with light or any other electromagnetic radiation. This makes it completely invisible and nearly impossible to detect with traditional telescopes or sensors. The idea that dark photons could offer a path to understanding dark matter is a tantalizing prospect, as it suggests that dark matter might not be as isolated from visible matter as we once believed. Dark photons could provide a new way of thinking about the relationship between normal matter and dark matter. If dark photons exist, they could be the missing link between these two realms, allowing them to interact in ways that were previously thought impossible. This could have far-reaching implications for our understanding of the formation of galaxies, the behavior of galaxy clusters, and even the distribution of mass across the universe. It could also open up entirely new avenues of exploration in particle physics, revealing deeper connections between the fundamental forces of nature. The potential for dark photons to revolutionize our understanding of the universe goes beyond just dark matter. Another area of great interest is the possibility that dark photons could be involved in the mysterious force of dark energy. Dark energy is the name given to the force responsible for the accelerated expansion of the universe. It is thought to make up around 68% of the universe's total energy density, yet its nature is completely unknown. If dark photons are able to interact with dark energy in some way, it could offer crucial insights into the nature of this force and how it is influencing the evolution of the universe. The connection between dark matter and dark energy has been the subject of much speculation in recent years. Some theories suggest that these two mysterious phenomena may be more closely related than previously thought. Dark matter and dark energy could potentially be different manifestations of the same underlying physical phenomenon, with dark photons acting as the mediators of the interactions between them. If this is the case, understanding the behavior of dark photons could be the key to unlocking the secrets of both dark matter and dark energy, providing a unified framework for understanding the unseen forces that shape the universe. While these ideas are still largely theoretical, the search for dark photons is providing new avenues for experimentation and observation. Advances in technology and instrumentation are allowing scientists to probe deeper into the cosmos than ever before, searching for signs of these elusive particles. Theoretical models are being refined, and experimental techniques are being developed to detect dark photons, even in the most challenging environments. Whether through astronomical observations of distant galaxies, high-energy experiments and particle accelerators, or novel methods of detecting cosmic rays, scientists are exploring a wide range of approaches to uncover the truth about dark photons. One of the most promising experimental efforts involves the use of precision measurements of electromagnetic interactions. Dark photons are theorized to interact very weakly with regular matter, but they may still influence the behavior of particles in subtle ways. By studying the way light interacts with matter at the quantum level, researchers may be able to detect the presence of dark photons. This could involve looking for tiny deviations in the behavior of particles or energy patterns that cannot be explained by known physics. The discovery of such anomalies would be a strong indicator that dark photons are indeed a real phenomenon, opening the door to a new era of exploration in particle physics. Another exciting possibility comes from the idea of hidden photons, a variation of dark photons that could be even more difficult to detect. These hidden photons are theorized to interact even more weakly with ordinary matter than regular dark photons, making them even more elusive. However, they could still have a detectable effect on the behavior of cosmic rays, neutrinos, or other high-energy particles. By studying these interactions in detail, scientists may be able to identify hidden photons and confirm their existence. This would provide further evidence of the existence of dark matter and its connection to the larger cosmos. The search for dark photons could also have practical implications beyond fundamental science. For example, understanding how dark photons interact with ordinary matter could lead to breakthroughs in materials science and technology. If dark photons are able to interact with matter in subtle ways, it might be possible to design new materials or devices that exploit these interactions. This could lead to advancements in energy storage, quantum computing, or other fields that are currently on the cutting edge of research. Despite the challenges, the potential rewards of discovering dark photons are immense. A breakthrough in this area could change the way we think about the universe, shedding light on the dark matter and dark energy that make up the vast majority of the cosmos. It could help us better understand the forces that govern the behavior of galaxies, the structure of the universe, and even the origins of space and time itself. In a sense, the search for dark photons is not just about uncovering the nature of a single particle. It is about unlocking the fundamental truths that underlie everything we know about the cosmos. The strange case of dark photons is one of the most intriguing and promising areas of research in modern physics. While their existence is still theoretical, the potential implications of dark photons are far-reaching and could have a profound impact on our understanding of dark matter, dark energy, and the fundamental forces that govern the universe. As scientists continue to explore the possibility of these elusive particles, they are not only pushing the boundaries of particle physics, but also challenging the very foundations of our understanding of the cosmos. The search for dark photons is a journey into the unknown, and it holds the promise of unraveling some of the deepest mysteries of the universe, mysteries that have remained hidden from our view for centuries. As we continue our exploration of dark photons, it's important to step back and consider how this concept fits into the broader picture of modern physics. The journey from classical physics to quantum mechanics, and from there to the most advanced theories of today, has been marked by discoveries that continuously reshape how we understand the universe. Dark photons, if proven to exist, could add another layer to this ever-growing narrative. The Standard Model of Particle Physics, which describes the fundamental particles and their interactions, has been an incredibly successful framework for understanding the nature of the observable universe. However, one of the key limitations of the Standard Model is its inability to explain dark matter and dark energy, which together make up about 95% of the total mass energy content of the universe. The remaining 5% that the Standard Model accounts for is what we see as ordinary matter, the stuff of stars, planets, and even ourselves. Dark matter and dark energy remain elusive, and they challenge our basic assumptions about the way the universe works. Dark photons enter the conversation as a potential solution to this enigma. If dark matter is indeed composed of some form of exotic particle that interacts through a different set of forces than ordinary matter, dark photons could be a way to connect these two worlds. Their theoretical framework suggests that dark photons would have a similar relationship to regular photons as dark matter does to ordinary matter. Both entities, though different in many ways, might be able to interact under certain conditions. In this way, dark photons could provide the missing link between the matter we can observe and the invisible dark matter that permeates the universe. This idea fits well within the broader field of theoretical physics, which often looks for hidden connections between seemingly disparate phenomena. Take, for example, the history of the search for the Higgs boson. For decades, the Higgs particle was just a theoretical concept, a necessary part of the Standard Model but impossible to observe directly. Then, in 2012, scientists at CERN's Large Hadron Collider confirmed the existence of the Higgs boson, completing a key puzzle piece of the Standard Model. In a similar way, dark photons could be a missing piece, one that helps us understand the fundamental forces of the universe and how dark matter interacts with the visible universe. However, unlike the Higgs boson, which was predicted and confirmed using existing frameworks and tools, the discovery of dark photons would require entirely new approaches. Unlike regular photons, which are massless and carry electromagnetic energy, dark photons would have a mass, but it would be extremely small. This would make detecting them with traditional methods incredibly challenging. Their interactions with ordinary matter would also be extremely weak, making them difficult to isolate in experiments. Despite these challenges, scientists are undeterred. They continue to refine their theoretical models and develop new experimental techniques to detect dark photons. Many of these efforts involve looking for very subtle anomalies in the behavior of light and other particles. In particular, dark photons might be detectable through their influence on the electromagnetic spectrum. For example, when light passes through a magnetic field, it can be altered in ways that are predicted by the Standard Model. If dark photons exist, they could cause additional, unexplained shifts or changes in this process, potentially offering a way to detect them. One experimental technique that has been proposed to detect dark photons involves the use of strong magnetic fields. The idea is that dark photons might interact with normal photons in a way that causes them to mix under certain conditions. In a laboratory setting, scientists can generate powerful magnetic fields and look for this potential mixing effect. The key challenge here is that the effects would be so subtle that they could easily be overshadowed by other physical phenomena. But if these dark photons are real, and if they do interact with normal photons, the right combination of experimental conditions might reveal their presence. Another experimental approach involves using large-scale cosmic observations. Some scientists believe that dark photons might be able to influence cosmic rays or other high-energy particles that travel through the universe. By studying the behavior of these particles, particularly in the vicinity of galaxies or other large gravitational sources, researchers might be able to detect the signatures of dark photons. This would require precise measurements of the cosmic background radiation, the behavior of galaxies, and the interactions of high-energy particles over vast distances. The potential discovery of dark photons would have profound implications, not just for cosmology and astrophysics, but also for our understanding of fundamental physics. It could provide a way to link the seemingly unobservable dark matter with the familiar world of ordinary matter. It might offer insights into the fundamental forces that govern the universe, revealing hidden interactions that were previously undetectable. Furthermore, it could revolutionize our understanding of the universe's evolution, from the very early moments of the Big Bang to the present day. In the realm of theoretical physics, the discovery of dark photons could lead to major breakthroughs in other areas as well. For instance, it could provide new insights into string theory, which posits the existence of extra dimensions beyond the familiar three of space and one of time. Dark photons, if they interact in ways that go beyond the known forces of the Standard Model, could be a clue that the universe is far more complex than we currently understand. In a similar vein, dark photons could also provide insights into quantum gravity, a field that seeks to combine the principles of quantum mechanics with the theory of general relativity. But perhaps the most profound impact of discovering dark photons would be the way it reshapes our view of the universe itself. For centuries, we have believed that the universe operates according to the laws of physics that govern ordinary matter, particles that we can observe and measure. But dark photons, if they exist, challenge that assumption. They suggest that there is much more to the universe than meets the eye, that there are hidden realms of matter and energy that interact with the observable world in ways we have yet to fully comprehend. This discovery could be the key to unlocking the deeper mysteries of the cosmos, helping us understand not just the past and present of the universe, but also its future. Furthermore, dark photons could help answer some of the most pressing questions in cosmology today. How did the universe evolve after the Big Bang? What is the true nature of dark matter? What is dark energy? And how does it influence the expansion of the universe? These are questions that have puzzled scientists for decades, and dark photons could be the missing link that brings all of these ideas together in a unified theory. The search for dark photons is more than just a scientific endeavor. It is an exploration of the unknown, a journey into the deepest mysteries of the universe. Whether or not dark photons exist remains to be seen, but the very pursuit of this question is pushing the boundaries of knowledge in ways that will likely yield new discoveries and breakthroughs for years to come. As scientists continue to investigate the potential of dark photons, they are not just looking for new particles, they are seeking to understand the fundamental nature of reality itself, and that is a quest that could change everything we know about the cosmos. As we continue exploring the potential of dark photons, it's essential to delve deeper into the philosophical and scientific implications of their existence. The notion of dark photons offers us an entirely new perspective on how we view the universe, a universe that, despite all our advancements, still holds mysteries far beyond our comprehension. The concept, while complex and theoretical, challenges the very fabric of our understanding of physics and could offer insights into some of the most fundamental questions about the cosmos. When we consider the possibility of dark photons, we're not just talking about a new particle in the traditional sense, but rather a new force or interaction that could fundamentally alter the way we view the forces that govern the universe. Currently, we understand four fundamental forces in nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. These forces govern everything from the smallest subatomic particles to the largest galaxies. However, the concept of dark photons suggests that there could be another layer of forces, unseen and unexplored, operating in parallel with these known forces. This hidden force, driven by dark photons, could open up a new chapter in our understanding of the universe, one where dark matter and ordinary matter are linked in ways that we've never before imagined. One of the central challenges in physics is reconciling the theory of general relativity, which governs the large-scale structure of the universe, with the principles of quantum mechanics, which govern the smallest particles. These two frameworks, while both successful in their respective domains, have not yet been unified into a single theory of quantum gravity. The discovery of dark photons could play a role in this quest for unification. Dark photons might be connected to new types of quantum fields that we haven't yet detected, fields that could reveal the hidden connections between gravity and quantum mechanics. In essence, they might provide the missing pieces needed to complete a theory that can explain both the large-scale behavior of the cosmos and the subatomic world. At the heart of this investigation lies one of the most intriguing questions in modern physics: what is dark matter? We know it exists because of its gravitational effects on galaxies and galaxy clusters, but we don't know what it's made of. The dark photon hypothesis suggests that dark matter might consist of a new class of particles, and dark photons could be the mediators of this dark matter. If dark photons interact with regular photons, they could cause the elusive dark matter to reveal itself in subtle ways, opening a window into this mysterious component of the universe. The search for dark photons is also intrinsically tied to the broader investigation of dark energy, the mysterious force that appears to be accelerating the expansion of the universe. Just as dark matter and ordinary matter are linked, dark photons might also have a connection to dark energy. If dark photons interact with dark matter and influence the universe's expansion, their discovery could provide clues to understanding why the universe is expanding at an ever-increasing rate. The relationship between dark energy and dark matter is one of the most profound puzzles in cosmology, and dark photons could be the bridge that links these two enigmatic forces together. However, despite the potential implications, detecting dark photons remains an incredibly difficult task. The fact that dark photons would be so weakly interacting with ordinary matter makes them elusive and challenging to observe. Even more so, their interactions might be so subtle that they could easily be overlooked in experimental data, making the hunt for these particles a complex endeavor. To make matters more complicated, the theory of dark photons itself is still in the early stages. The predictions for how they might interact with normal matter are varied, and scientists are still trying to pinpoint the most likely characteristics of dark photons that would allow for their detection. This uncertainty has led to the development of several different strategies to search for dark photons. Some experiments focus on detecting the subtle effects that dark photons might have on the behavior of photons in the presence of strong magnetic fields. Others look to cosmic rays or high-energy particles for any anomalies that might indicate dark photons' presence. Additionally, experiments at particle accelerators like the Large Hadron Collider, LHC, are also being used to search for dark photons by creating conditions where their effects might be detectable. The search for dark photons is not just about detecting new particles, but about pushing the boundaries of what we know about the universe. It's a search that requires creativity and persistence, as scientists attempt to measure the imperceptible, to see the unseen, and to discover the undiscovered. If successful, this search could provide answers to some of the most fundamental questions about the nature of the universe, from the makeup of dark matter to the ultimate fate of the cosmos itself. Moreover, the hunt for dark photons is not only a theoretical pursuit, it has practical implications for the future of physics and technology. The methods used to detect dark photons could also lead to advancements in other areas of science. For example, the tools and techniques developed to search for dark photons might be adapted to investigate other quantum phenomena, leading to new breakthroughs in materials science, communications, and computing. The search for dark photons could, in a very real sense, be the key that unlocks the next generation of scientific and technological advancements. In a broader sense, the discovery of dark photons would have profound philosophical implications. It would force us to confront the limitations of our current knowledge and rethink many of our assumptions about the nature of the universe. It would challenge us to reconsider the very foundations of physics, opening up new avenues of thought about the universe's structure, its origins, and its future. It would also remind us that there is so much more to the universe than meets the eye, that even in the most familiar and well-understood aspects of physics, there are still mysteries waiting to be uncovered. The implications of discovering dark photons extend beyond the scientific community, as well. If the search for dark photons is successful, it would be one of the greatest achievements in the history of science, comparable to the discovery of the Higgs boson or the detection of gravitational waves. It would not only answer some of the most profound questions in physics but would also expand the horizons of human knowledge, showing us just how much we have yet to learn about the universe in which we live. The concept of dark photons presents an exciting and potentially groundbreaking avenue for future research in physics. While the path to discovery is fraught with challenges, the rewards of understanding dark photons could be immeasurable. As we continue to probe the mysteries of the universe, dark photons may turn out to be the key that unlocks the hidden connections between dark matter, dark energy, and the forces that govern the cosmos. Whether or not we ultimately find them, the search itself is a testament to the boundless curiosity and ingenuity of the scientific community, And it serves as a reminder that there are always new mysteries waiting to be explored. As the search for dark photons presses forward, researchers are not only refining their methods but also expanding their theoretical frameworks. The discovery of dark photons would profoundly shift our current understanding of the universe, particularly in our ability to unify disparate forces and particles. One key area of focus for future research involves the potential interaction of dark photons with known particles, especially those related to dark matter. Imagine a universe where every particle we interact with, every object we observe, is part of a vast, hidden network of interactions, extending far beyond our current understanding of forces. This is the realm in which dark photons might exist. Theoretical models propose that dark photons could potentially interact with dark matter, creating a conduit between dark matter and the visible matter that makes up stars, planets, and everything we know. This interaction could occur through a concept known as kinetic mixing, where dark photons exchange energy with regular photons, thereby influencing the behavior of the dark sector of the universe. Kinetic mixing essentially describes the idea that dark photons could interact with the regular electromagnetic field via a kind of link, albeit weakly. This link could allow dark photons to gradually reveal themselves, providing indirect evidence of dark matter through small but detectable anomalies in photon behavior. These anomalies might occur under extreme conditions, such as when photons travel through high-energy environments, like those near a supermassive black hole or in the wake of high-energy particle collisions in laboratories. Interestingly, if dark photons are found to interact in this way, it could also imply that dark matter isn't as far removed from ordinary matter as we thought. Instead of being completely invisible or isolated, dark matter might have subtle effects on its surroundings, potentially influencing galaxies, star formation, and even the fundamental constants of nature. It would also give us the possibility of better understanding the true nature of the mysterious dark sector, which makes up roughly 85% of the mass in the universe. The search for dark photons could be likened to a treasure hunt where the prize isn't a tangible object, but rather a new understanding of the cosmos. And the significance of such a discovery would not just be for physicists or cosmologists. It would touch every corner of human knowledge. Our technological advancements, for instance, could leap forward. Consider how the search for the Higgs boson or gravitational waves has led to advancements in data processing and detection technologies. Similarly, detecting dark photons could spur innovation in fields like quantum computing, energy production, and even communications, as we learn to work with the properties of particles that interact so differently from those we're accustomed to. While we don't yet know if dark photons exist, or if they're even detectable by current or near-future technologies, scientists continue to develop more sophisticated tools to test these ideas. Large-scale experiments, such as those conducted at particle accelerators, remain essential in uncovering clues that could confirm the existence of dark photons. Additionally, astronomers are turning to telescopes and observatories in the hopes of uncovering indirect evidence of dark photon interactions, particularly in extreme cosmic environments. The intriguing thing about dark photons is that they represent a kind of unification of the unknown. In theory, they could bridge the gap between dark matter, dark energy, and ordinary matter, presenting us with a new kind of physics that integrates what we already know with what we haven't yet discovered. As research into dark photons progresses, the hope is that we will eventually uncover more than just a new particle or interaction. We may discover that the universe is far more interconnected and unified than we ever imagined, opening up an entirely new era in scientific discovery. But let's think about the implications beyond just the theoretical. If dark photons were confirmed to exist, it would challenge not only our understanding of physics, but our broader conception of reality itself. It would prompt us to re-examine the very concept of what it means for something to exist in the universe. After all, dark matter, and by extension, dark photons, exist only through their indirect effects on visible matter. They interact with regular matter in such subtle ways that their presence remains hidden, yet their influence is undeniable. In a sense, dark photons would force us to reconsider how we define the universe. Perhaps it's not just the sum of things we can see, touch, and measure, but the sum of everything that interacts with us, directly or indirectly. One of the more exciting aspects of this research is its potential to tie into other unsolved mysteries of the cosmos. For instance, the nature of cosmic inflation, the rapid expansion of the universe in its earliest moments, has puzzled scientists for decades. Could dark photons play a role in explaining this early expansion? Some models suggest that dark matter, and possibly dark photons, may have played a crucial role in shaping the evolution of the universe immediately after the Big Bang. By studying the behavior of dark photons, we may uncover clues to how the universe transitioned from a hot, dense state to the vast, expanding cosmos we observe today. Dark photons also intersect with another area of research, the search for a unified theory of everything. In the search for a grand unified theory, GUT, physicists seek to combine the forces of the universe into a single, overarching framework. While we have successfully unified the electromagnetic, weak, and strong nuclear forces under the Standard Model, gravity remains an enigma. Could dark photons, as mediators between dark matter and visible matter, play a key role in bridging this gap? Perhaps the forces that govern the very large and the very small, gravity and quantum mechanics, are more intertwined than we realize, and dark photons could provide the missing connection between these domains. However, even as we venture into these exciting theoretical realms, it's important to acknowledge that the road to confirming dark photons will not be easy. Detecting something as elusive as a dark photon requires not just the right experiments, but also the right mindset. The challenge lies not only in building better detectors but also in cultivating new ways of thinking about the interactions between matter and energy. Researchers will need to push the limits of current technology, adapting it to search for the faintest of signals that could hold the key to unlocking some of the most profound mysteries of the universe. Even more than that, the study of dark photons invites us to ponder deeper questions about the nature of science itself. What does it mean to know something? If dark photons can only be detected through their indirect effects, can we ever truly see them? And if dark matter and dark photons form the majority of the universe's mass, how do we reconcile this with the fact that we have been studying the universe primarily through the lens of visible matter? These are questions that don't just challenge the boundaries of physics. They challenge the very way we perceive and interpret the world around us. The search for dark photons is not just about uncovering a new particle. It's about redefining our place in the universe. It's a search that might not only change the way we understand the cosmos but also change the way we view our role within it. As we continue this exploration, we may come to realize that the true frontier of science is not out there in the vastness of space but in the unseen and the unknown, the particles, forces, and phenomena that remain just beyond our reach, waiting for us to discover them. As we continue exploring the potential of dark photons, it's crucial to consider the implications of their discovery on our broader understanding of the universe. For years, scientists have been attempting to bridge the gap between the known and the unknown. We've spent centuries expanding our understanding of visible matter, the matter that interacts with light, that we can see, touch, and measure. But this vast, observable universe only accounts for a small fraction of the actual content of the cosmos. Most of the universe is composed of dark matter and dark energy, both of which remain undetectable to the instruments we currently use. Dark photons represent a potential key to unlocking this vast, hidden realm, giving us access to a whole new dimension of cosmic phenomena. If dark photons are confirmed to exist, it would not only change our understanding of dark matter but could also rewrite the laws of physics as we know them. The fact that dark photons could interact with regular photons in specific conditions suggests that the divide between the dark and visible matter might not be as absolute as we thought. These interactions could offer us a direct means of studying dark matter through its effects on the more familiar electromagnetic spectrum, an area that's traditionally been off-limits for direct observation. Scientists are already working on several different experimental approaches that could test for the existence of dark photons. One avenue is through particle accelerators, where high-energy collisions might produce dark photons that could be detected through their influence on the behavior of other particles. These experiments could help reveal how dark photons interact with regular matter, giving us valuable insight into how dark matter behaves and how it might be manipulated or observed in the future. Another promising avenue involves astrophysical observations. cosmic phenomena, such as the interaction between high-energy photons and gravitational fields, could potentially provide clues about the presence of dark photons. One hypothesis suggests that dark photons might play a role in the cosmic microwave background (CMB), the afterglow of the Big Bang that carries a wealth of information about the early universe. By studying how photons behave in the CMB, scientists could detect anomalies that point to the presence of dark photons and, by extension, dark matter. If dark photons influence the CMB in any significant way, it could provide a direct, observational proof of their existence. Moreover, the search for dark photons is intrinsically linked to the search for a deeper understanding of dark matter itself. Dark matter, which makes up approximately 85% of the mass of the universe, is invisible, detectable only through its gravitational influence on visible matter. We've known for decades that dark matter exists because of its effects on galaxy rotation curves, gravitational lensing, and the movement of galaxy clusters, yet we still know very little about its actual composition. The discovery of dark photons would provide us with a tangible mechanism for understanding how dark matter behaves on a fundamental level, offering clues that could bring us closer to the ultimate goal of uncovering the nature of this elusive substance. Additionally, the concept of dark photons could help tie together disparate ideas in physics. For example, many physicists have long suspected that dark matter may not be a single, uniform substance but a complex mixture of different particles. Dark photons might serve as the missing link between these various components, helping us piece together a more complete picture of the dark sector of the universe. This could also lead to new discoveries in the realm of quantum field theory, as dark photons may behave in ways that challenge our current understanding of quantum interactions. But what if dark photons also play a role in something even more fundamental, such as the unification of the forces of nature? One of the most profound goals in physics is to find a unified theory that can explain all the forces of nature, from the gravitational force that shapes galaxies to the electromagnetic force that governs atomic interactions. Theories such as string theory and loop quantum gravity have made significant strides in this direction, but the discovery of dark photons might be the key to completing the puzzle. If dark photons interact with both dark matter and visible matter, they could represent a novel force that bridges the gap between different forces in the universe. This could help physicists achieve a long-sought goal, the unification of all the fundamental forces into a single, comprehensive theory. Such a discovery would have profound implications not only for our understanding of the universe but also for the very fabric of space and time. It could offer new ways of thinking about how the universe began, how it evolved, and how it may ultimately end. The confirmation of dark photons would suggest that the universe is far more interconnected than we ever realized, and that the boundaries between different types of matter, energy, and force are far more fluid than previously imagined. Yet, even with all the potential rewards, there are still many obstacles to overcome. The main challenge lies in detecting dark photons. Unlike regular photons, which can be detected through their interaction with matter, whether it's the way they carry energy to our eyes or how they are absorbed by detectors, dark photons are far more elusive. They interact weakly with regular matter, making them incredibly difficult to detect with our current instruments. Detecting dark photons requires an immense amount of precision and creativity, as well as an understanding of the nuances of how they might interact with both visible matter and dark matter. As the search for dark photons continues, one of the biggest hurdles is developing experiments that can rule out other possible explanations for any anomalies in particle behavior. After all, dark photons would interact so weakly with regular matter that any detection would likely be a subtle, indirect effect, something akin to detecting the faintest ripple in a vast ocean. And given that many other phenomena could produce similar effects, ensuring that these signals are truly the result of dark photons is no small task. Fortunately, physicists are not working in isolation. The search for dark photons is part of a larger, collaborative effort in the scientific community to understand the nature of dark matter. Researchers from a variety of fields, astrophysics, particle physics, cosmology, and beyond, are coming together to develop more refined tools and methods to test these theories. Through this collaboration, we may be able to overcome the technological and theoretical challenges that currently impede progress. The future of dark photon research holds much promise, and though we're still far from confirming their existence, every new experiment, every new observation, brings us one step closer to unraveling one of the universe's greatest mysteries. The discovery of dark photons would not only revolutionize our understanding of dark matter, but it could also spark a new era of exploration, one that could change everything we thought we knew about the nature of the universe itself. And as we venture further into the unknown, we're reminded of how much remains to be discovered. Perhaps the greatest mystery of all is not just what we will find in the search for dark photons, but what we will learn about ourselves and the universe we inhabit. It's a search that could reveal answers to questions we haven't yet thought to ask, and that might ultimately show us just how deeply interconnected everything in the cosmos truly is. As the search for dark photons continues, it becomes evident that this quest is more than just an academic pursuit. It represents a profound challenge to our understanding of the universe and how the very laws of nature operate. The nature of dark matter has remained one of the greatest mysteries of modern science. We've known for decades that it makes up the majority of the mass in the universe, yet we have no concrete understanding of its composition or behavior. Dark photons could be the breakthrough that finally sheds light on this dark, invisible sector of the universe. One of the exciting possibilities arising from the study of dark photons is that they could provide a new way to probe the relationship between matter and energy. This would be significant because, traditionally, these two concepts have been seen as separate. Energy, as we understand it, is what powers the processes that sustain the universe. Stars burn it, matter converts it, and life itself is fueled by it. Matter, on the other hand, is the substance that makes up everything in the universe. What if dark photons could help us understand how these two seemingly different concepts are interconnected, and possibly even how matter and energy might be more intertwined than we've previously thought? This question taps into the heart of modern physics, where the distinction between different types of matter and energy is becoming increasingly blurred. In string theory, for instance, what we think of as particles, such as photons, electrons, or even quarks, are not individual entities but vibrational modes of one-dimensional strings. These strings can exist in multiple dimensions beyond the familiar three-dimensional space that we observe. Could dark photons be another form of vibration, a new aspect of the hidden dimensions, that provides the key to understanding the fundamental structure of the universe? This is one of the many possibilities that researchers are considering as they look for ways to connect dark photons to the broader framework of quantum physics. As dark photon research progresses, scientists are also turning their attention to the potential impact that these discoveries could have on the development of new technologies. Understanding how dark photons interact with regular photons could eventually lead to new applications in fields such as communication and energy. For example, the ability to detect dark photons could open up new avenues for creating more sensitive detection systems, which could be used in everything from medical imaging to astrophysical research. Furthermore, understanding the behavior of dark photons could lead to breakthroughs in energy transmission and storage, potentially revolutionizing the way we generate and use power. But the implications of dark photons aren't just confined to theoretical physics or technological advances. The discovery of dark photons could have far-reaching consequences for our broader philosophical understanding of the universe. For centuries, humans have asked fundamental questions about the nature of reality, seeking to understand the structure of space, time, and matter. The existence of dark photons would suggest that there is a deeper, hidden order to the universe, one that extends beyond our immediate perception of the world around us. It would challenge our very notions of what is real and what is not, forcing us to rethink our place in the cosmos and how we relate to the unseen forces that govern it. At its core, the study of dark photons is a search for the unknown, a quest to uncover the mysteries that lie just beyond the horizon of human understanding. As scientists work tirelessly to probe the nature of dark matter and dark energy, the discovery of dark photons could mark a turning point in our comprehension of the universe. It might not only bridge the gap between normal and dark matter but also open up entirely new realms of scientific inquiry. One of the most intriguing aspects of dark photons is that they could potentially provide a new way to explain some of the most puzzling phenomena observed in astrophysics. For example, The mysterious behavior of galaxy rotation curves has long been a source of perplexity for scientists. When astronomers observe galaxies, they find that the stars on the outer edges of galaxies move much faster than they should according to the visible matter in those galaxies. This has led to the conclusion that there must be some form of invisible mass, dark matter, that is exerting gravitational influence on the stars. But what if the behavior of galaxies isn't solely due to dark matter? What if dark photons, through their interactions with regular photons, could play a role in shaping these rotation curves? Could it be that the dark sector of the universe, in conjunction with dark matter, influences how galaxies rotate and how their stars move through space? While this idea is still speculative, it opens up fascinating new possibilities for how we might interpret the data that we currently have on galaxy formation and behavior. Furthermore, dark photons could help explain the phenomenon of cosmic inflation. This refers to the rapid expansion of the universe in the moments following the Big Bang. Cosmic inflation is a key part of our current understanding of the early universe, but the details of how it occurred remain unclear. Some scientists have speculated that dark photons could have played a role in driving inflation, potentially providing an explanation for how the universe expanded so quickly in its infancy. If dark photons are confirmed to exist and are found to have such an influence on the early universe, it would provide a powerful new tool for cosmologists seeking to understand the origins of the cosmos. As we continue to explore the possibility of dark photons, we must also consider the broader context in which these discoveries are taking place. The search for dark matter, dark energy, and the unification of fundamental forces is part of a larger movement within the scientific community to unify the various aspects of physics. Whether through the search for dark photons, the study of string theory, or the investigation of quantum gravity, scientists are working toward a more complete understanding of the fundamental forces that govern the universe. The discovery of dark photons could be a crucial piece of this puzzle, offering insights that could lead to a more unified theory of everything, a theory that might one day explain all the forces of nature, from gravity to electromagnetism, in a single framework. Yet, as exciting as these prospects are, we must acknowledge the challenges that remain. The detection of dark photons is no easy task, and scientists are still grappling with the technological limitations of our current instruments. We have only begun to scratch the surface of what dark photons might reveal, and there are still many hurdles to overcome before we can definitively confirm their existence. However, the fact that we are even asking these questions is a testament to the incredible progress that has been made in the field of astrophysics and particle physics. As researchers continue to develop new methods for detecting dark photons and other dark matter candidates, it's clear that we are on the verge of a scientific revolution. The discovery of dark photons would not only answer some of the biggest questions in science but could also lead to new technological breakthroughs, offering us unprecedented ways to explore and understand the universe. The journey to uncover the mysteries of dark photons is far from over, and as we push the boundaries of knowledge, one thing is certain: the universe still holds many secrets, waiting to be discovered. The answers we seek may be hidden in the smallest of particles, in the faintest of interactions, or in the farthest reaches of the cosmos. But as we continue to ask questions and challenge our assumptions, the mysteries of the universe will slowly begin to unravel, revealing a deeper, more interconnected reality than we could have ever imagined. The discovery of dark photons could change the way we perceive the universe, especially in terms of the structure and interactions of different types of matter. If dark photons are found to be real, they could help explain why certain cosmic phenomena, like the behavior of galaxies and large-scale structures, have appeared to defy conventional understanding. The behavior of dark matter, for example, has been a major puzzle for scientists for decades. While dark matter cannot be observed directly, its presence is inferred by its gravitational effects on visible matter. Dark photons, if they exist, could offer a potential mechanism for dark matter's interaction with ordinary matter. This opens up the question: could dark photons also provide insight into the elusive dark energy? Dark energy is the mysterious force that appears to be causing the accelerated expansion of the universe, yet we know very little about it. Some theories propose that dark energy and dark matter are interconnected in ways that we haven't yet fully grasped. Dark photons, as hypothetical carriers of a force that could connect dark matter with normal matter, might help bridge the gap between these two phenomena, providing a more unified theory of cosmic forces. If dark photons indeed exist, we may eventually find that they are not just a bridge between normal and dark matter, but also a fundamental link between the forces that govern the expansion of the universe. In addition to offering explanations for cosmic phenomena, dark photons could help us further our understanding of fundamental physics on the smallest scales. Their potential as a new form of force carrier could revolutionize the way we think about particle physics. In the standard model of particle physics, the electromagnetic force is carried by photons, the weak force is carried by W and Z bosons, and the strong force is carried by gluons. If dark photons were to exist, they would be the force carriers for the dark sector, just as photons are for ordinary matter. This suggests that the universe may not be as simple as we once believed. Perhaps there are entire layers of reality that we have yet to discover, hidden dimensions, hidden particles, or unknown forces that shape the universe in ways we cannot yet observe directly. Dark photons could be a crucial clue to unlocking these deeper layers of reality, offering a way to probe the unknown forces that influence the cosmos. This is one of the most exciting possibilities that researchers are exploring as they continue their work in the dark matter and dark energy fields. Another area of potential application for dark photon research is in the search for new particles and phenomena beyond the Standard Model. The Standard Model has been incredibly successful in explaining most of the fundamental particles and forces that we observe in the universe. However, it leaves a number of unanswered questions, such as the nature of dark matter, the relationship between gravity and quantum mechanics, and the origin of the universe. Dark photons, if they exist, could be a way to extend our understanding of the Standard Model, providing insight into phenomena that do not fit neatly into our current theories. By studying dark photons and their interactions, we could uncover new realms of physics that challenge our current understanding of the fundamental nature of the universe. Moreover, the theoretical existence of dark photons ties into a broader framework of theoretical physics that seeks to unify the fundamental forces of nature. Currently, the four fundamental forces, gravity, electromagnetism, the weak force, and the strong force, are described by separate theories, with gravity standing apart from the others due to its lack of a quantum description. In this context, dark photons could play a significant role in bridging the gap between these separate theories. They may offer a clue to how the forces interact with one another, potentially contributing to the development of a unified field theory, a long-sought goal in physics that would describe all four fundamental forces in a single framework. The concept of dark photons also ties into more speculative theories, such as those involving extra dimensions. One of the most intriguing possibilities is that the universe may have more than the familiar three spatial dimensions and one time dimension. Extra dimensions, beyond those we can directly observe, could explain many of the mysteries of modern physics, including the behavior of gravity on large scales, the nature of dark matter, and the connection between different forces. Dark photons, if they exist, could provide a bridge between our familiar three-dimensional world and these hidden dimensions, offering us new ways to explore the fabric of the universe. As researchers continue to probe the mysteries of dark photons, it's clear that the quest for understanding the dark sector is only just beginning. With each new discovery, we push the boundaries of our knowledge further, uncovering new and unexpected insights into the nature of the cosmos. The path ahead is filled with challenges, and we are still in the early stages of unlocking the secrets that dark photons may hold. However, the potential rewards are immense. If dark photons prove to be real, they could open up entirely new fields of research, transforming our understanding of the universe and our place within it. The study of dark photons may also change the way we think about the fundamental nature of reality itself. For centuries, we have viewed the universe through the lens of classical physics, where the laws of nature are predictable and deterministic. However, the discovery of dark photons could show us that the universe is far more complex and interconnected than we ever imagined. It could challenge our assumptions about the structure of reality, forcing us to confront the possibility that there are hidden layers of the universe that we cannot yet observe, let alone comprehend. In many ways, dark photons represent the frontier of human knowledge. As scientists continue to search for evidence of their existence, they are pushing the boundaries of what we know about the universe and the forces that govern it. Every new discovery brings us closer to understanding the hidden forces that shape our reality, and dark photons may be the key to unlocking some of the deepest mysteries of the cosmos. The ultimate question that remains is whether dark photons will be detected, and if they are, what they will reveal about the universe. The search for these elusive particles is ongoing, and the future of this research promises to be as exciting and unpredictable as the cosmos itself. As we continue to probe the darkest corners of the universe, dark photons may just be the key that unlocks a new chapter in our understanding of the nature of reality. In the process, they may provide answers to some of the most profound questions humanity has ever asked. The story of dark photons is far from over, and as we continue to unravel the mysteries of the universe, we can be sure that our understanding of space, time, and matter will only deepen. With each new discovery, we will continue to challenge our preconceived notions about the universe, and perhaps, one day, we will uncover the true nature of the dark sector, a hidden world that has, until now, remained just beyond our reach. The intrigue surrounding dark photons is not just about their theoretical implications. It also sparks the curiosity about the tools and technologies that could one day detect them. As of now, there is no direct evidence for the existence of dark photons, but that hasn't stopped scientists from pushing the limits of detection. Many experiments are underway to explore the possibility that dark photons may be interacting with ordinary matter in ways we just haven't noticed yet. One of the primary methods for detecting dark photons involves high-energy particle collisions, like those conducted at particle accelerators such as the Large Hadron Collider, LHC. At the LHC, particles are smashed together at high speeds, recreating conditions similar to those shortly after the Big Bang. This allows researchers to look for anomalies in the data, unexpected interactions that might point to the existence of dark photons. However, since dark photons are expected to interact weakly with normal matter, detecting them requires an incredible level of precision and sensitivity. The challenge lies in distinguishing these potential interactions from the noise of other more common particles. In addition to particle accelerators, scientists are also using highly sensitive detectors to search for dark photons in cosmic rays. Cosmic rays are high-energy particles that travel through space and bombard the Earth's atmosphere. Some of these particles may be interacting with dark matter and creating dark photons in the process. Detecting these rare events is a monumental task, but it could offer some of the most direct evidence of dark photons and help to bridge the gap between dark matter and ordinary matter. Projects like the Dark Energy Survey (DS) and other large-scale astronomical surveys are already investigating cosmic rays and the potential role dark photons might play in these interactions. There is also the possibility that dark photons could reveal themselves through their effects on electromagnetic radiation. Since dark photons are predicted to interact with the electromagnetic field, they might cause subtle distortions or deviations in the behavior of light as it travels through space. Such distortions could be observed in the cosmic microwave background (CMB), the faint glow left over from the Big Bang. If dark photons exist, they could influence the way light travels across vast cosmic distances, providing us with an indirect way to detect their presence. Another avenue of research involves studying the interactions between dark photons and ordinary photons. In some theories, dark photons could couple with regular photons, leading to conversions between the two types of particles. This means that a regular photon could theoretically transform into a dark photon under the right conditions, and vice versa. This conversion process would be difficult to detect, but it could offer a potential signature of dark photons in astrophysical environments. Astrophysical phenomena such as the light emitted by distant stars or the behavior of matter near black holes could potentially provide indirect evidence of dark photon conversions, offering a way to study these mysterious particles in more detail. If dark photons are found, the implications for the future of science would be profound. We might be on the cusp of a major breakthrough in our understanding of the universe, one that could open up entirely new realms of physics and cosmology. Dark photons might not only help explain the nature of dark matter but also provide clues to the mysterious force known as dark energy. They could also shed light on the deeper structures of space-time itself, revealing hidden dimensions or forces that shape the universe in ways we never imagined. Moreover, the discovery of dark photons could lead to new technologies and applications in the future. Just as the discovery of the electron revolutionized the field of electronics, the identification of dark photons might give rise to new technologies that utilize their unique properties. These could include advanced sensors capable of detecting dark matter, or new methods of communication that exploit the interactions between dark and normal matter. The possibilities are vast, and while we are still far from understanding the full potential of dark photons, their study could unlock entirely new areas of technological development. The role of dark photons also connects to a broader conversation about the nature of reality. It is possible that, as we delve deeper into the physics of dark matter and dark energy, we may begin to question some of the most fundamental assumptions we have about the universe. The presence of dark photons could be a clue that there is more to reality than we currently perceive. Could it be that the very fabric of space and time is more flexible and interconnected than we think? Could dark matter, dark energy, and dark photons all be manifestations of some deeper, as yet undiscovered layer of reality? At the heart of this mystery is the idea that the universe is far more complex and interconnected than we could have ever imagined. As we uncover new particles, forces, and phenomena, we begin to realize that we may be on the threshold of a new era in science, one that challenges our deepest beliefs about the nature of the cosmos. Dark photons may be a key to unlocking the next chapter in our exploration of the universe. For now, however, the search for dark photons remains ongoing. Each new experiment, each new theory, brings us closer to understanding these elusive particles. While the road ahead is filled with uncertainties and challenges, the potential rewards are nothing short of extraordinary. The discovery of dark photons could not only revolutionize our understanding of dark matter and dark energy, but also offer new insights into the fundamental forces of nature. As scientists continue to explore the possibility of dark photons, the mystery of the dark sector deepens. The universe may be more mysterious and more interconnected than we have ever imagined, and dark photons could hold the key to unlocking the secrets of the cosmos. Whether or not we find definitive evidence for their existence, the pursuit of knowledge about these strange particles will continue to shape our understanding of the universe for years to come. The strange case of dark photons is just one piece of a much larger puzzle, a puzzle that stretches across the vastness of space and the depths of time. The mysteries of dark matter, dark energy, and the forces that govern the cosmos are far from solved. But the search for dark photons, and the potential they represent, could be the catalyst for a new era in science. An era where the boundaries of what we know about the universe are pushed further than we ever thought possible. We are only just beginning to understand the role that dark photons may play in the universe. The journey to uncover their secrets will take us into new realms of science, new frontiers of knowledge, and perhaps even new dimensions of reality. And as we continue this journey, one thing is clear: the universe is far stranger, more complex, and more interconnected than we ever imagined. Dark photons are just the beginning. As we continue to explore the potential of dark photons, it's important to realize how their discovery could reshape our understanding of the fundamental forces that govern the universe. Our current model of particle physics, the Standard Model, has been incredibly successful in explaining a vast range of phenomena. But as comprehensive as it is, it leaves many questions unanswered, particularly in the realm of dark matter, dark energy, and the potential connection between them. Dark photons, as a theoretical link between the visible world of ordinary matter and the unseen realm of dark matter, could be the missing piece that ties these puzzles together. One of the most intriguing aspects of dark photons is their possible connection to other exotic particles and forces. Theories involving dark matter often suggest the existence of particles that interact with regular matter via new forces or mediators. Dark photons are one candidate for this mediator role. If they exist, dark photons could interact with known particles through a force similar to electromagnetism but distinct in its effects. While regular photons mediate the electromagnetic force, dark photons would be responsible for a similar force operating in the dark sector. This hypothetical force could affect the behavior of dark matter, potentially offering a way for dark matter to influence the visible universe in ways that have yet to be directly observed. One of the reasons why dark photons are so compelling is their ability to explain some of the anomalies observed in astrophysical phenomena. For instance, certain observations of galaxy clusters, gravitational lensing, and cosmic ray behavior have hinted at the presence of unseen forces or particles that don't fit neatly into the current understanding of physics. Dark photons could potentially be responsible for some of these anomalies, acting as an invisible bridge between dark matter and ordinary matter. Their existence would not only help to explain dark matter's mysterious influence on galaxies and large-scale structures but could also open the door to understanding dark energy, a force that seems to be accelerating the expansion of the universe. Yet, there are challenges when it comes to testing these theories. As mentioned earlier, dark photons are theorized to interact extremely weakly with ordinary matter, which makes them incredibly difficult to detect. In fact, their existence would likely remain undetected unless they produce some observable effect, such as the transformation of regular photons into dark photons or the distortion of light from distant stars. However, even if these effects are subtle, the precision of modern instruments could one day be capable of detecting these faint signals. It's a race against time for scientists to develop the technology and methods needed to test these theories. A major breakthrough in detecting dark photons could come from the field of quantum sensors. These highly sensitive devices can measure tiny fluctuations in energy levels, magnetic fields, and other phenomena at incredibly small scales. With enough precision, quantum sensors could detect the minute interactions between dark photons and regular particles, providing evidence for their existence. Similarly, advances in astrophysical observation techniques, such as the study of cosmic microwave background radiation, could offer indirect evidence of dark photons by revealing subtle shifts or distortions in the cosmic radiation left over from the Big Bang. As we look to the future, it's also worth considering how the discovery of dark photons could impact our broader understanding of the universe's structure. The current understanding of physics assumes that the universe is governed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The discovery of dark photons would suggest the presence of an additional force, one that operates on the dark matter sector, perhaps in a way that is fundamentally different from the forces we currently understand. This could lead to a deeper investigation into the nature of the forces that bind matter together, possibly revealing new principles of physics that extend beyond the standard model. The potential for dark photons to connect dark matter and normal matter also has implications for our understanding of cosmology. Dark matter is believed to make up approximately 27% of the universe's total mass, yet it remains invisible and undetectable by traditional means. If dark photons exist, they could provide a mechanism for dark matter to interact with ordinary matter in ways that have previously been undetectable. This would allow us to test theories of how dark matter formed in the early universe, how it interacts with galaxies, and how it influences the large-scale structure of the cosmos. Dark photons could help explain why galaxies behave the way they do, why they spin at certain speeds, and why they form in the patterns we observe today. Dark photons could even provide insight into the question of why the universe exists in its current state at all. If dark matter and dark energy are connected in some way, the study of dark photons could help illuminate how the universe has evolved over billions of years. It could provide answers to why the universe is expanding at an accelerated rate, a mystery that has puzzled scientists since the discovery of dark energy. By uncovering the interactions between dark photons and ordinary matter, we could gain a better understanding of the forces driving this acceleration and perhaps even uncover the true origin of dark energy. But perhaps one of the most profound implications of discovering dark photons would be their potential to reshape the very way we think about the universe. It would challenge our understanding of space, time, and the fundamental forces that shape reality. If dark photons are proven to exist, it could open up new realms of physics that transcend our current models, offering glimpses into a hidden sector of the universe that has remained elusive for so long. It might even suggest that our current theories of physics are just the beginning, and that we are on the verge of uncovering a much deeper, more intricate web of connections that govern the universe. The pursuit of dark photons is more than just a scientific curiosity. It is a window into a deeper understanding of the cosmos. It is a quest that pushes the boundaries of human knowledge, challenging us to rethink what we know about the universe and what lies beyond the limits of our perception. As scientists continue to search for evidence of dark photons, they are not just trying to solve a specific problem. They are opening up new avenues of exploration that could one day lead to a radical shift in our understanding of the universe itself. We may not yet have the answers to the questions surrounding dark photons, but each new experiment, each new observation, brings us closer to understanding their place in the cosmic puzzle. If dark photons are real, they could be the key that unlocks some of the most profound mysteries of the universe, from the nature of dark matter and dark energy to the fundamental forces that govern everything we know. The search for dark photons represents the next great frontier in the exploration of the cosmos, one that could change our understanding of reality itself. And while we may still be far from confirming the existence of dark photons, the journey to uncover their secrets is already shaping the future of physics. As scientists continue to push the boundaries of what we know, we are reminded that the universe is far stranger, more complex, and more interconnected than we can ever truly imagine. The strange case of dark photons is just one piece of a much larger puzzle, a puzzle that may one day reveal a deeper, more intricate understanding of the cosmos and our place within it. As we continue this deep dive into the strange world of dark photons, it's important to pause and reflect on the vast implications their discovery could have for the future of science and humanity's understanding of the universe. The pursuit of dark photons is not just an academic exercise, it is a quest to fundamentally shift the way we view reality itself. If these particles do indeed exist and can be detected, they could serve as a key to unlocking some of the most profound mysteries of the cosmos, from the nature of dark matter to the very origins of the universe. In recent years, scientists have been increasingly focused on searching for ways to test the theory of dark photons. While we've outlined the many theoretical aspects and implications of dark photons, it's crucial to understand how they might eventually be detected in practical terms. One approach to detecting dark photons involves looking for their potential interactions with ordinary photons or charged particles. This would require specialized detectors capable of identifying subtle changes in the behavior of light or other particles as they travel through space or interact with matter. The idea that dark photons could couple with regular photons and alter their properties could allow scientists to detect their presence indirectly. For example, if dark photons interact with the electromagnetic field in some way, they could cause small shifts in the polarization or frequency of light emitted by distant stars or galaxies. These shifts might be incredibly faint, but with modern instrumentation, they could be observable. Advanced telescopes and detectors designed to measure cosmic radiation, such as those that already study the cosmic microwave background, CMB, or gamma ray bursts, might one day be repurposed or upgraded to search for these subtle effects. In fact, astronomers are already on the lookout for anomalies in the light from distant galaxies that could hint at the existence of dark photons. Moreover, experiments on Earth could provide additional clues. There are a number of particle accelerators, such as the Large Hadron Collider, LHC, that could potentially produce dark photons in the lab. These accelerators smash particles together at incredibly high energies, which may produce dark matter particles, including dark photons, in the process. Detecting these particles in a controlled laboratory setting would be a significant step forward in proving that dark photons are more than just a theoretical construct. As the search for dark photons intensifies, it's also worth considering the broader implications of such a discovery. If dark photons do exist, they could open the door to entirely new fields of physics that we have yet to imagine. For instance, they could provide a mechanism for explaining certain unexplained phenomena in astrophysics, such as the unusual behavior of galaxy rotation curves or the distribution of mass in galaxy clusters. These puzzles have long confounded scientists, and dark photons might provide the missing piece to solve them. But the potential of dark photons goes beyond just astrophysical mysteries. Their existence could have profound implications for our understanding of the fundamental forces that govern the universe. As we discussed earlier, dark photons are theorized to mediate a force between dark matter particles. This would mean that dark matter is not a static, invisible substance, it could be actively interacting with the rest of the universe through this dark force. This interaction might explain why dark matter behaves in such strange ways, influencing the movement of galaxies and the formation of cosmic structures without directly interacting with light. Furthermore, dark photons could provide a clue about the nature of dark energy, which is responsible for the accelerated expansion of the universe. The existence of dark photons could imply that dark matter and dark energy are not completely separate phenomena but might be linked through some deeper, more fundamental force. Understanding this connection could help scientists unravel one of the biggest mysteries of modern cosmology: why the universe is expanding at an ever-increasing rate. By studying dark photons and their interactions with dark matter, we could uncover a new layer of understanding about the dynamics of the universe on the largest scales. The discovery of dark photons would also have significant philosophical and metaphysical implications. For centuries, humans have struggled to comprehend the true nature of reality. What is the universe made of? What are the forces that govern its behavior? As we've learned more about the universe, we've uncovered more questions than answers. The discovery of dark photons would be another step in our ongoing journey to uncover the hidden truths of the cosmos. It could force us to reimagine the very fabric of reality and the fundamental principles of physics. We might need to revise our current models of the universe, expanding them to include a fifth force or a new form of matter that we previously didn't even know existed. This process of discovery could also inspire future generations of scientists to pursue careers in physics, cosmology, and astronomy. The search for dark photons, much like the search for dark matter itself, represents a new frontier in our understanding of the universe. It is a challenge that requires creativity, persistence, and innovative thinking. The very nature of dark photons, a particle that may or may not exist and interacts in ways that are still largely unknown, challenges scientists to think outside the box and approach problems from new perspectives. Moreover, the pursuit of dark photons could drive technological advancements that benefit not only physics but also other fields. The precision required to detect these particles could lead to innovations in measurement techniques, quantum sensors, and data analysis tools. These breakthroughs could have far-reaching applications in areas such as engineering, and even communications. After all, many of the most important technological advances in history have come about as a result of scientific research that was initially focused on solving fundamental questions about the nature of the universe. As we continue to search for dark photons, we must acknowledge that we are at the beginning of what could be a long and arduous journey. The evidence for their existence is still elusive, and we have much to learn about how to detect them. However, the excitement surrounding the possibility of discovering dark photons is palpable. The questions they raise, about dark matter, dark energy, and the fundamental forces of the universe, are among the most profound questions we can ask. By investigating these mysteries, we not only learn more about the universe but also about ourselves and our place in the grand scheme of things. The search for dark photons is about more than just finding a new particle. It's about deepening our understanding of the universe and challenging the very assumptions that underlie our current models of physics. It's about pushing the boundaries of human knowledge and expanding the horizons of what we think is possible. Whether or not dark photons are eventually discovered, the quest to understand them is a testament to humanity's relentless curiosity and our desire to uncover the deepest secrets of the cosmos. The continued pursuit of dark photons is not only an intellectual challenge, but also a philosophical one. As humanity's exploration of the cosmos moves forward, we find ourselves constantly redefining what we know about the universe, and the search for dark photons is a direct example of this. If we were to detect dark photons, it would essentially be like opening a door to an entirely new realm of understanding. Theoretically, these particles could offer a crucial missing link, enabling us to not only understand the nature of dark matter, but also to perceive the vast structure of the universe in an entirely different way. For a long time, we've been asking fundamental questions about the cosmos. What is dark matter? Why does it interact so weakly with regular matter? Why does it seem to govern the structure of galaxies and clusters, yet remain invisible? Dark photons offer a possible solution to some of these questions. Their discovery could radically shift the current paradigm, providing a more unified view of matter, energy, and the forces that shape the universe. To understand the full significance of dark photons, we need to revisit some of the unresolved problems in astrophysics that may be answered through their existence. One of the great mysteries of modern cosmology is the concept of dark matter. It is thought to make up about 27% of the universe, yet we have never observed it directly. Instead, we infer its presence based on its gravitational effects on visible matter, such as galaxies and galaxy clusters. If dark photons exist, they could interact with the particles that make up dark matter and mediate their behavior. This would allow dark matter to interact in subtle ways with the regular matter we are familiar with, potentially making it detectable in new ways. This is where the search for dark photons intersects with another great mystery, the behavior of galaxy clusters. Observations have shown that galaxies within clusters move faster than would be expected based on the amount of visible matter present. The gravitational pull from ordinary matter in these clusters doesn't seem to account for the observed velocities of galaxies. Scientists have suggested that dark matter is responsible for the additional gravitational pull. But if dark photons exist, they could play a role in the way dark matter interacts with regular matter, perhaps offering an explanation for the unexpected motion of galaxies. Moreover, the search for dark photons also ties into another fundamental question: the origin of the universe. The behavior of dark matter and the potential existence of dark photons might help us understand what occurred during the earliest moments of the cosmos. When we look at the large-scale structure of the universe, we see that galaxies and clusters are arranged in a vast web-like structure, which points to a process of cosmic evolution that started long before the stars and galaxies we see today began to form. Dark photons could be a key component in understanding how matter first came together, and how dark matter fits into the larger picture of the universe's evolution. The pursuit of dark photons may also offer an explanation for certain cosmic anomalies, such as the behavior of cosmic microwave background radiation, CMB. The CMB is the afterglow of the Big Bang, providing a snapshot of the universe's early state. It is remarkably uniform, but there are small fluctuations in temperature that could hold important clues about the nature of the universe. Dark photons, if they exist, could affect the way the CMB interacts with matter, leaving subtle signatures that might be detectable with the right technology. These fluctuations could tell us more about the early universe's conditions and the forces that were at play before stars and galaxies formed. As the search continues, it's important to recognize that while the concept of dark photons is still in the realm of theoretical physics, it has the potential to drive the development of new scientific tools and technologies. We are already seeing the fruits of technological innovation driven by fundamental questions. The quest to detect dark photons could lead to new advancements in particle physics, particularly in the development of more sensitive detectors and instruments that can measure minute changes in the behavior of light, electromagnetic fields, and even gravity. These innovations could, in turn, impact a wide range of fields. The possibilities of what a dark photon discovery could unlock are truly mind-boggling. The very existence of dark photons would force a complete overhaul of the standard model of particle physics, which has served as our guide to understanding the fundamental forces and particles that make up the universe. This model, while immensely successful in many ways, is not complete. It cannot explain certain phenomena, such as the nature of dark matter and dark energy, nor can it fully account for the behavior of gravity on cosmic scales. Dark photons could be the key to bridging these gaps. However, the road to finding dark photons will not be an easy one. It requires persistence, careful experimentation, and perhaps new ways of thinking about the forces that shape the universe. The scientific community must be open to new ideas and willing to embrace the unknown. The discovery of dark photons, should it occur, will likely take years, or even decades of searching. This is not a sprint but a marathon, a long journey into the unknown that could eventually provide answers to some of the most enduring questions in science. While dark photons remain a theoretical concept, the search for them is one of the most exciting frontiers in modern physics. The implications of their discovery would be profound, offering new insights into the nature of dark matter, dark energy, and the fundamental forces that govern the universe. This journey could reshape our understanding of reality itself, forcing us to rethink everything we know about the cosmos and our place within it. Whether or not dark photons exist, the effort to understand them will drive the scientific community forward, pushing the boundaries of human knowledge and perhaps one day answering some of the most profound questions of all. The pursuit of dark photons opens the door to several intriguing possibilities, not just in the realms of physics and cosmology, but in broader scientific and philosophical areas as well. For example, one of the more mind-bending possibilities that could arise from the discovery of dark photons is the potential for a new type of communication. In theory, if dark photons can interact with the particles of regular matter, then they might be harnessed as a method for transferring information through the universe. Since dark matter and its associated phenomena are thought to make up a large portion of the universe's mass, the discovery of a way to utilize dark photons could revolutionize the way we think about communication over cosmic distances. This concept is particularly fascinating when considered in the context of space exploration. Imagine being able to communicate across vast distances, even in regions where traditional electromagnetic radiation cannot reach. If dark photons can travel through regions of space that are opaque to ordinary light, they might offer a means of maintaining communication with spacecraft or colonies far from Earth, potentially providing a method for interstellar communication. This idea, while speculative, underscores the transformative impact that the discovery of dark photons could have not only in our understanding of the universe, but also in the technological advancements that could arise from it. On a more theoretical level, the existence of dark photons could force us to reconsider the way we categorize and understand the fundamental forces of nature. The search for dark photons is an investigation into the very nature of reality, and discovering these particles would introduce a new kind of force, something that would be distinct from the four known forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. This additional force, possibly mediated by dark photons, could offer an entirely new framework for understanding how the universe operates on a fundamental level. One of the most profound implications of dark photons lies in their potential connection to dark energy. While dark matter is thought to account for the missing mass in the universe, dark energy is the mysterious force driving the accelerated expansion of the cosmos. If dark photons are a real phenomenon, they might offer a way to connect these two enigmatic components of the universe. For instance, if dark photons can interact with both dark matter and dark energy, they might provide a unified explanation for some of the strange behaviors of the universe at the largest scales. This could lead to a new understanding of the universe's past, present, and future. Despite the exciting possibilities, it is important to acknowledge the challenges that come with the search for dark photons. Currently, the detection of dark matter, let alone dark photons, is still one of the greatest obstacles facing modern physics. There are several experiments being conducted worldwide that aim to detect dark matter and dark energy indirectly, such as through the study of cosmic rays, gravitational lensing, or even the faint signals left behind by dark matter collisions. However, these methods have yet to yield definitive results. This means that the search for dark photons is, at present, still in its infancy. However, that doesn't mean that scientists are not actively pursuing new methods of detection. There are numerous ongoing efforts to design more sensitive detectors that could pick up on the faintest signs of dark photons, if they exist. For example, some researchers are exploring the use of lasers to stimulate dark photons, while others are looking at the possibility of detecting dark photons through the effects they might have on electromagnetic fields, or the cosmic microwave background radiation. The search is relentless, and new advancements are being made all the time, slowly but surely expanding the horizons of what is possible in the realm of particle physics. Additionally, the search for dark photons raises several fascinating questions about the fundamental nature of particles and forces. In a universe where so much remains hidden from view, the discovery of dark photons would not only answer questions about dark matter but could potentially provide answers to even deeper mysteries. How do these particles interact with one another? Do they play a role in the formation of galaxies, stars, and other cosmic structures? Could they offer insights into the early moments of the Big Bang, when the universe was still in its infancy? As the scientific community continues its search for dark photons, we are likely to encounter more questions than answers. Yet, this is the nature of scientific progress. With every discovery, more questions arise, pushing us to think deeper and challenge our assumptions about the universe. In a sense, the search for dark photons reflects the very spirit of scientific inquiry, constantly striving to uncover the unknown and expand our understanding of reality. The ultimate detection of dark photons would not just be a scientific milestone, it would be a cultural milestone. The implications for humanity's place in the universe would be profound. The discovery of dark photons would symbolize the moment when we bridge the gap between what we can see and what we cannot. It would challenge our understanding of matter, energy, and even time itself. Just as the discovery of radio waves, X-rays, and other forms of radiation expanded our understanding of the electromagnetic spectrum, so too could dark photons open up entirely new ways of exploring the cosmos. Furthermore, this discovery would likely have practical applications beyond the realm of theoretical physics. Understanding how dark photons work could lead to breakthroughs in other areas of science and technology. For example, their potential to interact with dark matter might allow scientists to develop new techniques for exploring the deepest reaches of the universe. It could also have more immediate implications for technologies such as sensors, communication devices, and energy systems, by providing a new framework for how we interact with and manipulate fundamental particles. Dark photons, however, also have an air of mystery that extends beyond their theoretical implications. They are a prime example of how the universe constantly presents us with new puzzles that challenge not only our scientific knowledge but also our philosophical and metaphysical assumptions. The existence of dark photons forces us to ask big questions. What is the nature of reality? How much do we truly understand about the forces that govern the universe? And most intriguingly, are there even more particles, forces, or realms that we have yet to uncover? The case of dark photons is a perfect example of the awe-inspiring journey of scientific discovery. We stand on the precipice of something potentially groundbreaking, yet the answers we seek may lie in realms far beyond our current capabilities to detect or understand. The search for dark photons is not merely a search for a new particle, it's a quest for deeper knowledge, an endeavor that could change the very fabric of our understanding of the cosmos. As we continue to explore the mysteries of dark matter, dark energy, and the universe as a whole, the quest for dark photons will remain a cornerstone of our investigations. Whether they are ultimately discovered or not, the pursuit of dark photons will undoubtedly expand the boundaries of our scientific imagination and may, one day, unlock the final pieces of the cosmic puzzle. The potential discovery of dark photons is not merely a pursuit for physicists alone, but one that has implications for all of humanity. It offers a glimpse into a more profound understanding of the universe, challenging our assumptions and expanding our conceptions of what reality itself might be. The journey of exploring dark photons is one that connects the microscopic with the cosmic, the theoretical with the practical, and the known with the unknown. We have already made tremendous strides in understanding the nature of the universe, but the discovery of dark photons could mark a new frontier in this endless pursuit. One of the reasons dark photons are so compelling is the way they could bridge the gap between our known universe and the mysterious dark realm. Right now, dark matter and dark energy are abstract concepts, almost impossible to detect directly. While we observe their effects on large-scale structures like galaxies and galaxy clusters, the true nature of these invisible entities remains elusive. However, if dark photons are indeed the missing link between visible matter and dark matter, they could offer the key to unlocking these hidden phenomena. What's so remarkable about dark photons is that they are theorized to interact with both regular matter and dark matter in ways that traditional photons cannot. Unlike ordinary photons, which are the carriers of electromagnetic force and interact primarily with electrically charged particles, dark photons would interact with the hidden dark sector. In this way, they could serve as the connection between the ordinary world of visible matter and the enigmatic realm of dark matter. This means that dark photons could allow us to study dark matter more directly, bypassing some of the limitations of current detection methods. Instead of merely inferring the presence of dark matter through its gravitational effects on visible matter, We might one day be able to detect the direct signatures of dark photons in laboratory experiments. As of now, one of the primary challenges in the search for dark photons is that we have no direct evidence of their existence. Scientists have no clear way of detecting them, as they are thought to interact with matter only weakly. However, this doesn't mean they're beyond detection. It simply means that our current technology and techniques aren't sensitive enough to detect them yet. There is hope that new advancements in experimental technology will eventually open the door to their discovery. For example, scientists are working on highly sensitive detectors that could potentially observe the faintest signals of dark photons, even if these particles interact with matter in a way that makes them difficult to detect. The role of dark photons in explaining the larger mysteries of the universe, such as the nature of dark matter and dark energy, could be profound. Dark matter, which makes up approximately 27% of the universe's mass, does not emit light or other forms of electromagnetic radiation, making it virtually invisible to our instruments. Its existence is inferred primarily through its gravitational effects on visible matter, such as the rotation of galaxies. While we have a solid understanding of how dark matter affects the behavior of galaxies, we have no clear understanding of what dark matter is made of or how it interacts with other particles. This is where dark photons could play a crucial role. In the current framework of physics, the interaction between dark matter and ordinary matter is still a mystery. However, dark photons could provide a way for dark matter to interact with the normal matter that makes up the world we see around us. If dark photons exist, they could allow us to explore dark matter directly, shedding light on one of the most elusive and mysterious substances in the universe. This could also pave the way for new theories in particle physics and cosmology, potentially offering a unified framework for understanding both visible and invisible matter in the universe. Moreover, dark photons could have a deeper connection to the mysterious phenomenon of dark energy. Dark energy, which is thought to account for around 68% of the total energy content of the universe, is responsible for the accelerated expansion of the cosmos. While we have a reasonable understanding of the gravitational effects of dark energy, its true nature remains unclear. If dark photons are involved in the interaction between dark matter and dark energy, they could offer a way to connect these two enigmatic forces, offering new insights into how the universe is expanding and how it will evolve in the distant future. In addition to their potential to reveal more about dark matter and dark energy, dark photons could also help us better understand fundamental physics, such as the nature of the four fundamental forces. As mentioned before, the four known fundamental forces are gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Each of these forces is mediated by particles known as force carriers, e.g., photons for electromagnetism, gluons for the strong force. If dark photons are indeed real, they could serve as the carrier particles for a new, fifth force that interacts with both dark matter and regular matter. This would radically change our understanding of the universe and the forces that govern it. While the theoretical implications of dark photons are vast, so too are the potential practical applications. For instance, if dark photons are discovered and can be manipulated in laboratory settings, they could have a wide range of technological applications. This could include advancements in communications, energy systems, and even medical technologies. As we continue to explore the properties of dark photons, we may find that they offer new ways of interacting with the universe and harnessing its hidden potential. The possibilities are vast, and each new discovery brings us closer to a deeper understanding of the universe. The search for dark photons, and the broader investigation into dark matter and dark energy, represents one of the most exciting frontiers in modern science. While the existence of dark photons remains speculative, the pursuit of their discovery is a testament to humanity's unyielding curiosity and desire to unlock the secrets of the universe. In many ways, the search for dark photons is emblematic of the larger scientific quest to understand the cosmos, an endeavor that is far from easy, yet filled with immense potential for discovery. While we may not yet have direct evidence of dark photons, their potential to transform our understanding of the universe cannot be overstated. They could provide the key to understanding dark matter, dark energy, and even the fundamental forces of nature. The implications of their discovery would be far-reaching, extending from fundamental physics to practical applications that could change the way we interact with the world around us. As we continue to push the boundaries of our knowledge, dark photons remain one of the most intriguing mysteries in modern science, a puzzle that could one day unlock the deepest secrets of the cosmos. The ongoing investigation into dark photons is a testament to the fact that the universe is far more complex and mysterious than we could ever have imagined. As we probe deeper into the nature of dark matter, dark energy, and the very forces that govern the universe, dark photons could emerge as one of the most transformative discoveries in modern physics. The implications stretch beyond academic curiosity. They have the potential to alter the course of scientific inquiry, opening up new avenues for exploration and technological advancement that could shape the future of humanity. As the search for dark photons progresses, we are reminded of how much we still have to learn. The theoretical foundations of dark photons are built on the assumption that these particles are a manifestation of a larger, more complex, dark sector, which operates in parallel with the visible world that we experience. This dark sector could contain its own set of forces, particles, and interactions, separate from the known forces that govern the behavior of ordinary matter. If dark photons are indeed real, they would be the first evidence of this hidden world, offering a glimpse into a realm that has remained invisible to our senses. The idea of a dark sector is not entirely new. In fact, many physicists have proposed theories suggesting the existence of such a sector. These theories arise from the realization that our current understanding of particle physics, particularly the Standard Model, is not complete. The Standard Model describes the particles and forces that make up the observable universe, but it fails to account for several key phenomena, including the presence of dark matter and dark energy. The dark sector hypothesis seeks to address these gaps by proposing that dark matter, dark energy, and potentially even dark photons exist in a parallel framework, interacting with our world in ways that we are only beginning to understand. The potential role of dark photons in this dark sector could be profound. These particles would be the first known carriers of force within this hidden realm. Just as ordinary photons mediate the electromagnetic force between particles in the visible universe, dark photons could serve a similar function within the dark sector, facilitating interactions between dark matter particles. This would not only provide a direct link between ordinary matter and dark matter but could also shed light on the nature of dark energy, which remains one of the greatest mysteries in cosmology. Despite the exciting possibilities, there are significant challenges in detecting dark photons. As mentioned earlier, these particles are theorized to interact with matter only weakly, which makes them extremely difficult to detect using current experimental methods. The sensitivity of our instruments is a key limitation. Dark photons could easily pass through conventional detectors without leaving any trace. However, this does not mean that the search is in vain. Scientists are constantly developing more sophisticated techniques and experimental setups in hopes of capturing even the faintest signal from these elusive particles. For instance, experiments that measure the interaction of particles in high-energy environments, such as those conducted at particle accelerators like the Large Hadron Collider, LHC, are among the most promising avenues for detecting dark photons. These experiments involve smashing particles together at incredibly high speeds, creating conditions similar to those that existed just moments after the Big Bang. In these extreme environments, scientists hope that dark photons could emerge as a byproduct of these high-energy collisions. By carefully analyzing the results of these experiments, researchers might be able to detect subtle signals of dark photon interactions, revealing their existence for the first time. While the odds are slim, every new experiment increases the chances of a breakthrough discovery. Another promising approach involves the use of astrophysical observations. The cosmos provides a natural laboratory for studying dark matter and dark energy. Researchers have speculated that dark photons could leave an imprint on the cosmic microwave background, CMB, which is the afterglow of the Big Bang. If dark photons exist, they might interact with other cosmic particles, creating subtle distortions in the CMB. By studying these distortions, scientists could gain valuable insights into the properties of dark photons and their role in the early universe. Additionally, dark photons could potentially be detected through their effects on the behavior of galaxies and galaxy clusters, providing a link between fundamental physics and astronomical observations. The potential discovery of dark photons would not only revolutionize our understanding of dark matter and dark energy, but could also have far-reaching implications for the field of particle physics as a whole. If dark photons exist, it would suggest that there are forces and particles beyond those currently described by the Standard Model. This would be a game-changing discovery, forcing physicists to rethink long-held assumptions about the nature of reality and the fundamental forces that govern it. The very concept of a dark sector would challenge our understanding of space and time, suggesting that the universe is far more intricate and multidimensional than we have previously imagined. Furthermore, dark photons could provide a new path forward in our quest to unify the fundamental forces of nature. One of the major goals of theoretical physics is to develop a theory that combines the four known fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, into a single, unified framework. This theory of everything has long been a holy grail for physicists, but it has proven to be incredibly elusive. The discovery of dark photons could bring us closer to this goal by revealing a deeper connection between the forces of the visible universe and the hidden dark sector. By understanding how dark photons interact with other particles, scientists may be able to uncover new relationships between the known forces and the mysterious forces that govern dark matter and dark energy. In addition to their theoretical importance, dark photons could also open up new possibilities for practical applications. While the primary motivation for studying dark photons is to gain a deeper understanding of the universe, these particles could also have real-world implications. For instance, dark photons could potentially be used in the development of new technologies that harness the properties of dark matter or dark energy. While this may sound like science fiction, history has shown that breakthroughs in fundamental physics often lead to unexpected technological advances. The discovery of the electron, for example, led to the development of modern electronics, and the discovery of quantum mechanics paved the way for technologies like lasers and computers. In a similar vein, the discovery of dark photons could lead to entirely new fields of technology that we cannot yet fully imagine. Ultimately, the search for dark photons is more than just an academic exercise. It is a quest to understand the fundamental nature of the universe itself, a pursuit that has the potential to reshape our understanding of everything from the smallest particles to the largest cosmic structures. Dark photons represent the bridge between the visible world and the invisible realm of dark matter and dark energy. By unlocking the secrets of these elusive particles, we could open the door to a new era of scientific discovery, one that may reveal a universe far more complex and interconnected than we have ever dreamed. As the search for dark photons continues, we are reminded that the universe is full of mysteries waiting to be uncovered. Each discovery, no matter how small, brings us one step closer to understanding the vast and intricate tapestry of reality. The strange case of dark photons is just one chapter in this ongoing adventure, but it is a chapter that could change everything. If dark photons are out there, waiting to be discovered, the implications for science and technology are limitless. The pursuit of this discovery is not just a scientific endeavor, it is a journey into the heart of the cosmos itself, where the answers to some of our most profound questions may lie hidden, waiting to be revealed. As we continue to explore the strange and fascinating world of dark photons, the implications stretch even further into areas we never anticipated. These particles are a theoretical cornerstone in our understanding of the elusive dark sector, but they also hold immense promise for the future of physics, cosmology, and technology. The ongoing research into dark photons could be the key to solving some of the most profound puzzles that have puzzled scientists for centuries. Let's take a step back for a moment and reflect on what makes dark photons so intriguing. Unlike their more familiar cousins, the ordinary photons that mediate electromagnetic forces, dark photons are theorized to interact only with dark matter and potentially other particles in the hidden sector. This stark difference in behavior could explain why we have never been able to observe them directly. They are simply not in the same, visible, realm as the particles we are accustomed to studying. Yet, this lack of direct interaction with ordinary matter could also make dark photons a window into a completely new and unexplored domain of physics. The idea of dark matter itself was a mystery for decades before scientists came to accept that it must exist, simply based on its gravitational effects on visible matter. If dark photons do exist, they would be the first real proof that dark matter isn't just an invisible, inert substance. Instead, it may have an active role in the universe, interacting with itself and potentially influencing the behavior of normal matter in ways we still don't fully comprehend. The discovery of dark photons would help to cement dark matter as not only real but dynamic, challenging our traditional views of the cosmos. When we begin to think about how dark photons might interact with the known universe, we begin to see the potential impact they could have on our understanding of fundamental forces. At its core, the existence of dark photons could lead to the development of entirely new theories that describe the relationships between dark matter, dark energy, and ordinary matter. These relationships could uncover new forces or new interactions that we are only just beginning to scratch the surface of. Imagine a world where we are able to harness the power of dark photons. With the right understanding, it could revolutionize the way we think about energy and matter. Technologies based on the properties of dark photons might one day enable us to interact with dark matter directly, potentially leading to advancements that are currently the stuff of science fiction. Whether it's new energy sources or unprecedented methods of communication, the applications of dark photon research could be limitless, although it would require many years of work and breakthroughs to fully realize. However, the road ahead is long and challenging. Even if dark photons do exist, it will take years of cutting-edge research and technology development to detect them with certainty. Current experiments are incredibly sensitive, but they are still unable to directly observe dark photons. Instead, scientists are using indirect methods, looking for signs of dark photon interactions or phenomena that could give clues as to their existence. These indirect methods include searching for anomalies in the cosmic microwave background, studying the behavior of galaxy clusters, and observing the interactions of particles in high-energy environments such as those created at particle accelerators like the LHC. The sensitivity required to detect dark photons is immense, and for now, their existence remains a theory. But the theory itself is exciting enough to fuel decades of exploration. Dark photons could play a central role in shaping the future of particle physics, potentially leading to a deeper, unified theory of forces, particles, and interactions. If they are detected, it could represent one of the most significant breakthroughs in physics since the discovery of the Higgs boson. However, the reality of dark photons may be even more profound, as we begin to understand the hidden dimensions of our universe, one layer at a time. One of the most fascinating aspects of dark photons is the way in which they may tie into other unproven theories, such as supersymmetry and string theory. Supersymmetry, for instance, proposes that every particle has a superpartner, with similar properties but differing in key ways, such as mass. The discovery of dark photons could be a major step toward verifying supersymmetry, and this could unlock entirely new realms of physics. Similarly, dark photons might offer insights into string theory, which posits that the fundamental particles of the universe are actually tiny, vibrating strings. If dark photons are real, they could serve as a bridge between the standard model and these larger, more exotic theories. Furthermore, dark photons may also help explain phenomena like the anomalous behavior of galaxies and galaxy clusters. In our current understanding, dark matter is thought to explain these strange cosmic behaviors, but dark photons could offer a deeper explanation of how dark matter interacts and moves. For example, dark photons might interact with the dark matter in such a way that they alter the gravitational effects we observe in galaxies. These subtle interactions could change the way dark matter clusters and could provide new insights into how large structures in the universe form and evolve. Beyond their scientific implications, the detection of dark photons would also have enormous cultural significance. The discovery of dark matter itself was a revolution in the way humanity thinks about the universe. Dark photons would be another milestone in our understanding, offering concrete evidence that there are entire realms of the cosmos that remain beyond our traditional methods of observation. It would show that our universe is far more complex and multi-layered than we could have ever dreamed, and it would invite us to rethink what is possible in terms of physics, technology, and even human potential. So, where do we go from here? The hunt for dark photons is in its infancy, but every step forward brings us closer to an answer that could change everything. Whether it's through advanced experiments at particle accelerators, observations of the cosmos, or new theoretical insights, scientists are racing against the clock to unlock the secrets of the dark sector. And with each discovery, we are one step closer to understanding the most fundamental questions about the universe, dark matter, and the forces that shape everything around us. The strange case of dark photons is not just a theoretical curiosity. It is a potential game-changer that could redefine our understanding of the universe, lead to groundbreaking technologies, and reveal a hidden world of particles, forces, and interactions. The implications for physics, cosmology, and technology are far-reaching, and as we continue to explore the mysteries of dark matter, dark energy, and the dark photons themselves, we are reminded of just how much we still have to learn. The universe, with all its hidden secrets, is far from fully understood, and dark photons may be one of the keys to unlocking its deepest mysteries. As we continue to explore the possible existence of dark photons, it's essential to dive deeper into how these particles could influence not just the theoretical landscape of physics, but also our understanding of the universe at large. The journey into the hidden realms of the cosmos, where dark photons may reside, is one that challenges everything we think we know about the nature of reality. But before we get ahead of ourselves, let's take a moment to consider just how radically dark photons would change our current view of the universe. Imagine a world where we can directly probe the dark sector, a world where the mysterious forces and particles that comprise the bulk of the cosmos are no longer invisible. Dark photons are more than just a theoretical prediction. They are a glimpse into an entirely new frontier of science, one that could ultimately lead to a complete rewriting of the laws of physics as we know them. The detection of dark photons would not just confirm the existence of dark matter, but it could also open up an entirely new branch of physics, potentially unifying the known forces of the universe with those still hidden from our view. Now, let's delve into how scientists are currently working to test the hypothesis of dark photons. The main challenge here is their extremely weak interaction with ordinary matter. Unlike the familiar photons that we can observe with telescopes, dark photons are thought to interact primarily with dark matter and possibly with other particles in the dark sector. This makes direct detection exceedingly difficult. To find dark photons, physicists must look for indirect evidence of their presence, signals that may indicate their existence without directly seeing them. One of the primary ways researchers are searching for dark photons involves particle accelerators, like the Large Hadron Collider, LHC. These accelerators can produce conditions where exotic particles might emerge. In particular, dark photons could be produced in high-energy particle collisions. When two particles collide at extremely high speeds, they can create a shower of new particles, some of which may be dark photons. While detecting these dark photons directly might be impossible, scientists can look for the decay products or other effects that occur when these particles interact with normal matter. By carefully analyzing the energy patterns and the way particles behave in these experiments, researchers can infer the presence of dark photons. Another promising avenue involves astrophysical observations. Dark photons could have an influence on the way light travels through space, potentially altering the cosmic microwave background radiation or distorting light from distant galaxies. These subtle changes, while incredibly difficult to detect, might offer indirect proof of dark photons. Researchers are constantly studying these cosmic phenomena to spot any anomalies that could be linked to the existence of dark photons. In addition to experiments at particle accelerators and astrophysical observations, dark photons could potentially be detected through their interactions with other particles in the laboratory. One possible experiment involves using magnetic fields to search for shadows of dark photons. Since dark photons are believed to have a small mass, they might behave somewhat like ordinary photons in a magnetic field, but with some important differences. By using highly sensitive detectors, scientists might be able to identify these tiny differences and detect the presence of dark photons. Even though the search for dark photons is still in its early stages, it's worth noting the profound implications this research could have if successful. For one, confirming the existence of dark photons would not only prove that dark matter exists, but it would also suggest that the dark sector of the universe is more intricate and interconnected with the observable universe than we had previously realized. Dark photons could potentially be the missing link between dark matter and ordinary matter, helping to bridge the gap between the visible and invisible components of the cosmos. What makes dark photons particularly interesting is that they are not just a theoretical curiosity. They could potentially solve some of the most perplexing mysteries of the universe. For example, dark photons could help explain the elusive nature of dark matter. Current models suggest that dark matter interacts with ordinary matter gravitationally, but otherwise remains largely invisible. However, if dark photons do exist, they could mediate additional forces between dark matter particles. This would mean that dark matter is not entirely passive, but could have its own internal dynamics, making it far more interesting and complex than simply an inert substance. Moreover, dark photons might also provide insight into the nature of dark energy. As we've discussed earlier, dark energy is thought to be responsible for the accelerated expansion of the universe. If dark photons exist, they could play a role in shaping the properties of dark energy and its interaction with dark matter. The discovery of dark photons could open the door to a deeper understanding of how dark energy works and how it drives the expansion of the universe. Theoretical models of dark photons also have far-reaching implications beyond just understanding dark matter. For example, some researchers have suggested that dark photons could help explain certain anomalies in physics that have yet to be explained, such as the nature of the missing antimatter in the universe. The existence of dark photons could provide a new framework for understanding how matter and antimatter interact, and why the universe seems to be dominated by matter rather than antimatter. In addition, dark photons might play a role in solving some of the most fundamental questions in physics, such as the nature of the fine-tuning problem in cosmology. Fine-tuning refers to the observation that the constants of nature, such as the gravitational constant, the speed of light, and the strength of the electromagnetic force, are set to values that allow for the existence of life. If dark photons exist, they could help explain why these constants are so finely tuned and whether they are the result of some deeper, more fundamental theory. But what would the practical implications of discovering dark photons be for our everyday lives? While this may sound far-fetched, the understanding of dark matter and dark photons could have a profound impact on technology. Take, for example, the field of communication. If we can harness the properties of dark photons, we might one day develop new communication technologies that use the dark sector of the universe. This could lead to ultra-secure communication methods that are practically immune to interference. Theoretical advances in quantum computing might also be accelerated by a deeper understanding of dark photons, leading to entirely new kinds of computational power. The technological applications of dark photon research are vast, but they remain speculative for now. What is certain, however, is that any breakthrough in the search for dark photons would mark a monumental shift in our understanding of the universe. It would suggest that the forces and particles that govern the cosmos are far more complex than we ever imagined. And who knows? The discovery of dark photons could open the floodgates to a new era of technological and scientific innovation, one that challenges our very understanding of reality. As we reach the end of our journey into the strange case of dark photons, it's clear that these elusive particles could hold the key to unlocking some of the universe's greatest mysteries. Their potential impact on physics, cosmology, and technology is immense, and the search for dark photons is only just beginning. While we may not yet have definitive proof of their existence, the theoretical framework is in place, and scientists around the world are working tirelessly to uncover the truth. Whether dark photons are real or not, the pursuit of this mysterious particle is a testament to the power of human curiosity and the unyielding desire to understand the universe at its most fundamental level. In the coming years, as technology advances and experiments become more sophisticated, we may just find the evidence we need to confirm the existence of dark photons and open a new chapter in the history of science. As we continue to explore the strange case of dark photons, it's essential to reflect on just how far we've come in our understanding of the universe and how much further we have to go. Every new discovery, every new theory, opens up more questions than it answers. But that's the beauty of science. It's a never-ending quest for knowledge, a journey through uncharted territory. The search for dark photons is one such journey, and it's unfolding in real time, right before our eyes. One fascinating aspect of dark photons is their potential relationship with another dark sector phenomenon, dark energy. As we know, dark energy is the mysterious force that accelerates the expansion of the universe. But what if dark photons are, in some way, related to dark energy? Could these particles somehow interact with dark energy in a way we haven't yet imagined? The idea that dark photons could be linked to dark energy would completely reshape our understanding of the cosmos, providing a unified theory that connects dark matter, dark energy, and possibly other unseen forces in the universe. The speculative nature of dark photon theory is something that sparks both excitement and skepticism in the scientific community. While many physicists are eager to explore the dark sector, the fact remains that dark photons have yet to be directly detected. This absence of proof, however, is not an argument against their existence. In fact, the very nature of dark matter and dark energy is that they are elusive, interacting with ordinary matter only in the faintest, most indirect ways. Their discovery would not be a straightforward triumph of observation, but rather a leap of faith in the power of theoretical physics and its ability to predict the unseen. This is where the most exciting aspect of dark photon research lies: the theoretical groundwork. The predictions made by scientists, though speculative, are grounded in rigorous mathematical models and backed by observations of the cosmos. These models suggest that dark photons could be coupled with ordinary photons via a new force, one that we've never seen before. This force, which could manifest in the form of new interactions, could bridge the gap between the ordinary and dark sectors. Imagine a force, invisible yet powerful, that connects the visible universe with the dark side, where most of the universe's mass resides. It's the stuff of science fiction, but it's also grounded in theoretical physics. In addition to their theoretical implications, dark photons could also offer a potential solution to some of the most puzzling observations in modern cosmology. For instance, the nature of galaxy rotation curves has long been a mystery. When astronomers observed galaxies, they found that their outer regions were rotating faster than predicted by the laws of gravity and visible matter. This discrepancy led to the hypothesis of dark matter, an invisible substance that exerts gravitational effects but doesn't interact with light. However, the exact nature of dark matter remained elusive. Dark photons could potentially play a role in explaining these unexpected behaviors. If dark photons were interacting with dark matter in such a way that they influenced the gravitational effects seen in galaxies, it could explain some of the discrepancies in galaxy rotation curves. It's a tantalizing possibility, one that could offer a fresh perspective on a long-standing problem. Another exciting avenue for dark photon research is its potential connection to the enigmatic phenomenon of cosmic inflation. Cosmic inflation refers to the rapid expansion of the universe just moments after the Big Bang. This expansion was so fast that it stretched space-time itself, creating the vast universe we see today. The details of this process remain somewhat mysterious, with only theoretical models to guide us. However, the interaction of dark photons with the fabric of space-time could offer new insights into how inflation worked and how it shaped the universe. In terms of testing dark photon theories, the scientific community is relying on both experimental and observational methods. On the experimental side, particle detectors like those at the Large Hadron Collider, LHC, are crucial tools in the search for dark photons. These machines can recreate the extreme conditions necessary to produce dark photons, providing a way to detect their faint interactions with other particles. However, as we've already discussed, detecting dark photons is far from simple. Their weak interaction with ordinary matter makes it incredibly challenging to isolate them from the overwhelming noise of more familiar particles. This is where observational astronomy plays a vital role. By examining phenomena like the cosmic microwave background (CMB), which is the afterglow of the Big Bang, scientists hope to spot subtle imprints of dark photons. These imprints could manifest as tiny distortions in the radiation pattern, revealing the influence of dark photons on the fabric of the universe itself. Similarly, astronomers are looking for indirect evidence in the form of gravitational waves, cosmic radiation, and even the behavior of galaxy clusters. Each of these could hold the key to uncovering dark photons and, by extension, the nature of dark matter and dark energy. As we look to the future, it's clear that the hunt for dark photons is just beginning. The tools we have at our disposal are growing more powerful with each passing year, and our understanding of the dark sector is becoming increasingly sophisticated. The detection of dark photons would be one of the most groundbreaking discoveries in the history of science, potentially unlocking the secrets of dark matter, dark energy, and the fundamental forces that govern the universe. But it's not just about the dark photons themselves. The search for these particles is a testament to the strength of human curiosity and the drive to understand the unknown. It shows that even when faced with the vastness of the universe and the mysteries that lie within it, we persist. We keep asking questions, keep developing new theories, and keep pushing the boundaries of what we know. The story of dark photons is not just about a particular particle, but about the human spirit of exploration. It's about venturing into the unknown, confronting the mysteries of the universe, and refusing to settle for easy answers. It's about seeing the invisible and making the invisible visible, no matter how elusive or distant it may seem. We may not yet have found dark photons, but the journey to uncover them is a journey worth taking. Each step, each experiment, each new theory brings us closer to the answers we seek. And in the process, we are learning more about the very fabric of reality itself. So, as we continue to look into the vastness of space and explore the strange case of dark photons, let us remember that every mystery we uncover is a step toward a deeper understanding of the universe. A universe that is far more strange, complex, and beautiful than we ever could have imagined. The search for dark photons may one day lead us to a new chapter in the story of science. One where the boundaries between the known and the unknown blur, where the forces of the universe that were once hidden from view are brought into the light. And when that day comes, we will know that the journey was worth it, because the mysteries of the cosmos are not just puzzles to be solved, but gateways to a deeper, more profound understanding of existence itself. As we continue to delve deeper into the mysteries of dark photons, it's essential to grasp the broader implications of their possible discovery. If dark photons are indeed real, their existence would signify a seismic shift in our understanding of the universe. The idea that there could be another fundamental force, one that links the visible and invisible sectors, would challenge everything we thought we knew about physics. It would essentially open the door to a new realm of science, one where the laws of nature are more complex, and perhaps even more interconnected, than we could have imagined. Think about the implications for particle physics. The Standard Model, which is the cornerstone of our understanding of particle interactions, has been incredibly successful in explaining most of the forces and particles we observe in the universe. However, it has been clear for decades that the Standard Model is incomplete. It doesn't account for dark matter, dark energy, or gravity in the way we need. If dark photons exist, it would suggest that there are more forces at play than we've recognized, forces that could help bridge the gap between our current understanding and the unknown. This could lead to a new version of the Standard Model, one that incorporates dark matter, dark energy, and other unseen forces into a more unified theory of the universe. Additionally, the discovery of dark photons could provide clues about the very nature of the universe's expansion. We've already established that the universe is expanding, but the rate of expansion is accelerating, which suggests the presence of dark energy. If dark photons were discovered, it might offer a new perspective on this accelerated expansion. Perhaps dark photons are involved in this process in some way, influencing the cosmic fabric in ways we have yet to understand. This could provide a better understanding of why the expansion is happening at such a rapid pace and whether there are mechanisms in the dark sector that are driving this acceleration. Another fascinating angle is how dark photons could offer new insights into the formation and evolution of the universe itself. We know that the early universe was a hot, dense place, filled with particles and radiation. During this time, interactions between particles would have been governed by a variety of forces. If dark photons were a part of these early interactions, their presence could explain certain features of the universe's early stages, such as the formation of the cosmic microwave background, CMB, and the distribution of matter. Understanding how dark photons might have played a role in these processes could reveal key details about how the universe evolved from a chaotic, violent place into the expansive, structured cosmos we observe today. And as we've touched on before, dark photons could help explain the behavior of galaxies. For years, astronomers have been puzzled by the observed movement of galaxies, particularly how their outer regions rotate faster than expected based on the visible matter we can see. This observation led to the hypothesis of dark matter, an unseen substance that doesn't emit light but has a gravitational influence on visible matter. Could dark photons be part of this mysterious dark matter? It's possible that they could interact with dark matter in a way that contributes to these unusual rotational speeds. By understanding how dark photons might influence the behavior of galaxies, we could gain a better grasp of the role dark matter plays in the universe. In addition to the scientific and theoretical aspects, the search for dark photons also has profound philosophical implications. For centuries, humanity has looked to the stars, searching for answers to the biggest questions of existence. The discovery of dark photons, and the potential it holds for unifying our understanding of dark matter and dark energy, would be a major milestone in our quest for knowledge. It would show that we are capable of uncovering the hidden layers of reality, even those that are completely invisible to our senses. It would be a testament to the ingenuity and persistence of human beings, who, despite the vastness of the unknown, continue to push the boundaries of what we know and explore the depths of the cosmos. As exciting as the possibility of dark photons is, there's still a long way to go before we can say with certainty that they exist. There are many challenges ahead. For one, the experimental detection of dark photons is incredibly difficult. Their weak interaction with matter means that they are almost impossible to detect using conventional methods. Researchers are relying on advanced technologies and indirect methods of observation, like the study of cosmic radiation and the cosmic microwave background, to find clues. But even with the most advanced tools at our disposal, the search for dark photons will likely be a slow and painstaking process. It may take years, or even decades, before we have enough evidence to confirm their existence. But the pursuit of dark photons is a testament to the power of scientific curiosity. The fact that scientists are willing to dedicate years of their lives to exploring a theoretical concept with no direct evidence of its existence shows the passion and commitment to understanding the universe. It's a reminder that science is not just about answers, it's about the process of discovery. It's about the thrill of the unknown, the excitement of uncovering something that could fundamentally change our understanding of reality. In the meantime, there are plenty of other exciting developments to keep an eye on in the field of dark matter and dark energy research. New telescopes and detectors are being developed to explore the dark sector, and experiments like those at the Large Hadron Collider, LHC, continue to search for signs of dark photons and other exotic particles. Every breakthrough brings us one step closer to understanding the vast, invisible universe that surrounds us. As we reflect on the strange case of dark photons, we are reminded of the vastness of the unknown. There is so much we still don't understand about the universe, from the tiniest particles to the largest cosmic structures. The search for dark photons is just one piece of this larger puzzle, a puzzle that is continually evolving as new discoveries are made. But even if we don't find dark photons in the immediate future, the journey itself will be worth it. It will be a journey of exploration, discovery, and wonder, a journey that brings us closer to the fundamental truths of the universe. So, as we continue to watch the skies and search for the elusive dark photons, let's remember that the pursuit of knowledge is never in vain. Every question we ask, every theory we propose, brings us closer to understanding the most profound mysteries of the cosmos. The strange case of dark photons is just one chapter in the ongoing saga of our exploration of the universe. And as we venture further into the unknown, we can only wonder what other secrets the cosmos holds, waiting to be uncovered by the curiosity and determination of those who dare to ask the big questions. The discovery of dark photons, should it ever come to pass, will be one of the greatest triumphs in the history of science. It will show us that even the most elusive, mysterious forces of the universe can be understood, at least in part, through the lens of human ingenuity and perseverance. And as we move forward, We can rest assured that the journey to uncover the secrets of the cosmos will continue to inspire generations to come, reminding us that the greatest discoveries often lie just beyond the horizon, waiting to be discovered by those who dare to look. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.